Hey, Etienne, how are you?
Hi.
Nice to see you. It's been a while.
Hi, Anton. Yeah, good.
Just wanted to quickly test my audio to see if people can hear me.
Yeah.
Great, thank you.
Just test the. Okay.
Yeah, okay.
Dear colleagues,
Hello.
I'm glad to see you here as a participant of our conference, and I
Hi,
hope
Oleg.
all will be successful.
Thank you. Good to see you.
Also, well, Yurina, hello. I'm glad to see you here. How are you?
Nice.
Hi.
You are ready?
I'm ready every day. Good morning, everybody. 9 o'clock, and we start, please.
Thank you. So let me share my screen.
And this is Greg Gbur. I'm one of the chairs of the session. I'll probably just give you like a 5-minute warning before the end, just in case things are running over.
No. Guess it's good like this.
That looks good from our end, I think.
So let me know when I will start.
Okay. Yeah, I guess co-moderating this session or chairing this session with is it Professor Mokhun, and I think we can go ahead and get started. Our first talk is structured wave plates for multidimensional beam shaping.
Thank you, Greg. So I'm happy to share this presentation with you. I thank Oleg for keeping on with the spirit of this event, of this singular event at singular places all over the years. And I guess as everyone here, we wish all to be there next time live. My talk is entitled Structured Wave Plates for Multidimensional Beam Shaping. It's a work done at Laboratoire en des Matières d'Aquitaine and in Bordeaux, France. And the main idea here is to discuss some of our recent results during the last 2 years regarding beam shaping. Whenever the polarization and the spatial degrees of freedom of light are involved. And regarding the multidimensional aspect of the talk, this concerns the way to handle the spatial degrees of freedom and the frequency degree of freedom. And at the end of the presentation, as well, the combination of space plus frequency. So let me start with the outline of the presentation. So I will start with very general words regarding the vortex beam generation, which is the particular focus we choose in our research in this topic, but it could be extended to other kind of beams. The main point is to address what I call here the modal issue. So I will introduce modes and I will further explain why and in which direction we are progressing to answer this modal issue I will define. Then I will present the ingredients, the main ingredient through a case study, the main ingredient used to shape the light fields the way we want, meaning in a modal way. And then I will address the how this spin-orbit interaction actually can be used to take control over the two-dimensional spatial degree of freedom when dealing with two-dimensional fields, so within the paraxial approximation. And eventually, I will end with some recent results on the emergence of new functionalities, which were, I would say, not much, admittedly, anticipated, but that we found, and that open new perspective, in my opinion, or at least in the way we will carry out near future research. So all starts with the Maxwell's equation when dealing with light. And when I will talk about light beams, light fields, all of them will pertain to the well-known paraxial approximations, and for which we can decompose the field, any paraxial field, so defining z-axis as the main propagation direction, as a collection of modes, here represented as a sum of weighted function depending on r phi z, the cylindrical coordinate chosen here, and these are the well-known Laguerre-Gauss modes. And so once we said that, we just said that okay, we have a way to mathematically describe in an exact manner any kind of light field. And if we look closely, the way the functions, the modal elements, ULP, which are all orthogonal one to another, behaves as a function of the polar coordinates in the transverse plane, we see the emergence of optical phase singularity, which means here the optical vortices. And this is the scope of this is the main ingredient we will use. And the point is that apart I would say the common place Gaussian beam indexed with azimuthal index L0 and the radial index P0. Of course, we have an infinite basis, both for the azimuthal degree of freedom and for the radial degree of freedom. And the main idea here is to realize that when we're in the lab, I would say since the early days of beam shaping to obtain optical phase singularity, this was mainly done using so-called helical phase masks. And these phase masks actually, once placed in the course of an incident Gaussian beam, whatever its polarization state, and centered on the center of the mask, where the phase is helically growing around the central place of the plate. This is the real space propagation. So you place the plate here, the phase masks, pure phase masks. There is a typical characteristic transverse extent of the beam, the waist W0 here. And this is the way diffraction occurs as light propagates further from the origin, which is the plate plane. And of course, as indicated here, pure helical phase modulation is not enough to obtain modal shaping. It's enough to obtain a vortex beam, of course, because we have imparted the AEL phi here, L equal 3 phase profile to the beam. However, there is an infinite superposition of radial modes, P modes. And of course, in a far field, again in the lab, one could think at first sight that this donut-shaped optical vortex beam does look like Laguerre-Gauss mode. However, it is not. People are well aware in the community about that and develop tools to obtain real optical mode whenever an optical information encoded in the two-dimensional degree of freedom transverse plane is necessary. So here on the left, on the right, the slide, you see how the far field depart from the actual Laguerre-Gauss beams once normalized and matching the maximum intensity location. So this means that there is a need for developing tools in order to obtain modes. Vortex modes. And if we get a closer look, a quantitative look to how the energy is spread into the radial dimension, I would say, let's have a look to this simulated bar plot, which exemplify how the energy is distributed around in the plane of parameter L and P for a given vortex, given hologram L, which imparts helical phase mask to an incident Gaussian beam. And here we see that, of course, if we have starting with a Gaussian beam with a unit waist value 1, of course, this one is fully developed as a mode. However, passing through a plate with L equal 1 or more, we see that there is a distribution of P modes that appears at the expense of a reduced P0 L contribution. And this shows two things. This plot shows two things. As you can see here, this simulation is carried out for what is called an optimum waist size used for the decomposition. Actually, we have to recall that the Laguerre-Gauss beams basis does depend on the choice of a beam waist parameter. So this is important. What we call an optimal decomposition is that for which the targeted mode has the maximum weight once the decomposition is carried out. The second point on which we will further elaborate is the fact that actually to cope with these radial losses, radial mode losses, the idea is to have complex modulation. And this complex modulation for the amplitude implies to work both with phase and amplitude and to shape both at once in order to have right after the plate the correct complex field amplitude corresponding to a Lagrange beam. So nowadays we have a lot of options to do that, and the most used one is certainly reconfigurable holographic technologies. And here just show just a picture of a device. It's typically 10 centimeter size. I would say spatial volume taken on the optical table, and these usually are megapixel devices, and the amplitude or the phase of such devices, such device allow to individual control of amplitude and phase with a good spatial resolution. And here I will address another way to do modal beam shaping, not exploiting directly the brute force modulation of amplitude or phase via light modulator, but using the polarization state of light as a way to achieve spatial light modulation. And here comes the spin-orbit interaction of light, so which I will introduce, at least to be on the same page, even for those used to it, with a case study. The case study is the simplest situation of the optical problem of what is the field after half wave plate. So plate imparting pi phase retardation difference between two orthogonal polarization, accounting for psi angle as the orientation of the optical axis of this plate, which is an anisotropic slab of material, pure transient material. So the idea is like take a circular polarization, quadrature orthogonal linearly polarized component X and Y, and after the plate, of course, the pi phase shift between these two components implies that the plate allows to flip the helicity sigma from one value to the opposite value, whatever its initial value, and simply change the handedness of the circular polarization state. If we look closely in this case of plane wave description, how the field is transformed, how the amplitude, the complex amplitude is transformed after passing through the plate, we obtain the following expression. An incident circular polarization state is transformed up to pure phase amplitude factor associated with the propagation through the plate. Here we recognize the mean optical phase path, and this is called the dynamic phase. And there is a second term, a second phase term associated this time with the orientation of the optical axis of the plate in the transverse plane. And of course, the polarization state has been flipped. And so in general, we are dealing with a combination of structural phase and a propagation phase, dynamic and geometric. And if we go in the framework of vortex beam generation, as again the main ingredients to construct Lagrange beams, the idea is simply to wrap the half wave plate into the structural topological defects for the optical axis orientation in such a manner in order to have a half integer or integer multiple of the polar angle for the orientation. And this is I would say well known since 20 years, since Lorenzo Marucci exemplified this using liquid crystals patterned. And in that case, we obtain geometric spiral phase plates. So at this point, we just reach another way to obtain a pure helical phase masks. And this is what we get. This is a picture, a cartoon representing the way the wavefront is shaped in a helical manner regarding depending on the incident spin states. However, those elements, as just recalled, as associated with the wavefront having pure helical phase masks. As such, as said before, they are intrinsically non-modal spin-orbit optical elements. So there is a good point. We have a spin control of the phase singularity topological charge. However, we are not addressing specifically L and P mode in the Laguerre-Gaussian phase space. And this leads me to discuss how the spin-orbit interaction can be used in order to tailor the Laguerre-Gauss beam shaping. So the works I will present belong to the research developments we carry out at Bordeaux with Vagarchak Akopian, who is presently in his PhD development. And also, depending on the work, many collaborations have been involved, in particular, one with Peter Kazakhstan, Optical Research Center in UK, Guixin Li at SUSTEC, Shenzhen, China, and Andrew Forbes at WITS, South Africa. So I will now develop this a bit further. So this is a general expression of how the circular polarization state is transformed after a spin orbit, a vortex plate as presented just before. As we said here, the optical axis distribution is shaped in a way that we will get the sought after Laguerre-Gauss helical phase. And in the case presented before, and the usual case that, for instance, you can buy such plates from many providers nowadays. They are all used for, or all designed and operate in a half wave plate condition, where the birefringent phase retardation here, capital delta, is equal to pi. So of course, this is addressing a specific wavelength, since the birefringent phase is proportional to the inverse of the wavelength. But in the general case, if it's detuned with respect to the operating wavelengths, this is the expression that you get. And the idea is to exploit the possible imperfection of what I would call a detuned wave plate, structured wave plate, in order to shape the Laguerre-Gauss amplitude. So the idea is to exploit the possible phase variation of the birefringent phase retardation in order to shape the amplitude of the field and reaching modality. However, there is a price to pay. The price to pay is adding a polarizer, a circular polarizer, selecting, projecting the output field on the contrast circular polarization state with respect to the input circular polarization state. Once you are ready to do so, then you are simply stating what you want. An incident Gaussian beam, which is a usual beam coming out of lasers. And then you want simply to place your plate and just after to have a mode. So for that, you are prescribing that the amplitude right after the plate should be of this shape up to and the helical phase being addressed by this term. So here, related to the amplitude, we want that the Laguerre-Gauss beam shape is that of the Gaussian beam multiplied by the modulating factor in front of the contracircular component. And then if we want to explore non-zero P modes, in that case, we have to manage this radially oscillating pi phase change, which are sine plus minus 1 change as one evolves along the radial coordinate. To reach non-zero P, and this is simply achieved by making jumps of the orientation in a zonal manner. So this is a recipe we proposed a couple of years ago, and this is the way we realized it. So the idea is to use a structured plate where we can tune, where we can design and prepare space variant retardance with space variant optical axis orientation of a given optically anisotropic medium. So the first example I'll show here corresponds to the femtosecond laser structured silica. And the idea being to send a pulse beam with appropriate dose, repetition rate, pulse durations in order to shape to process the silica and to impart silica with nanostructured, and then that will make the material behaving as an effective anisotropic medium with a given optical axis controlled by the writing beam polarization azimuth, and whose anisotropy strengths will be controlled by how strongly the interaction takes place. And this is what we get. Here on the left, the standard wave plate, the usual one, a structured wave plate. You can see it's highly transparent, and here you just see my finger in between which you have the plate, which is typically a few millimeter diameter. And the modal plate look like this between cross-linear polarizers. So the structured plate is just here, it's nicely non-scattering optical elements, it's good quality, and we are ready to demonstrate it works. So here is the summary. We will simply illuminate these plates. There's a given circular polarization state and observe the contrast circular polarization, however, taking care of projecting to get the appropriate modal shaping. And this is what you get. So this is a standard wave plate as we were previously introduced. And here is the modal vortex shaper. As you can see, right after the plate, which is placed here on the left of each panel, the donut shaper is immediately obtained. It's a compact device, and then you have simply the usual diffraction of the beam. And here are the three plates we were dealing with. If you look closely, at least qualitatively, to appreciate the modality gain from the usual to the modal strategy, we just here plotted the radial profile and simply renormalized all of them along the radial coordinate to the maximum intensity value. And you see the usual spreading associated with a huge content regarding the radial mode degree of freedom. And here you see a more packed distribution of the shape, which is highlighting the shape invariant propagation of Lagrange beams. However, it's not perfect, as you were seeing. So the idea is to be back to the general expression and to realize that the price to pay to impart the material with a spatially variant anisotropic value is to have a dynamic phase, which also depends on the radial coordinate. Indeed, it is actually difficult to change the anisotropy of the material without changing its mean refractive index, which means without changing the dynamical phase it imparts to the light field passing through. So to solve this problem, we recall that we have a geometric phase degree of freedom. And by changing the structure of the optical axis spatial distribution, we can actually correct the unwanted radially modulated dynamic phase modulation in order to recover, at the end of the day, a proper Lagrange mode for the contrast circular component. So this has been made within the development of a second generation of Lagrange spin orbit plates. And this is the result between the observation of the second generation, which is a corrected one, and here is the first generation, the uncorrected one, for different topological charge, L. And so between cross-circular polarizers, one can appreciate the space variant birefringence, so no big change about fine detail is observed. And regarding another level of detail, simply by changing the polarizer using cross-linear polarizers, you can already appreciate that the structure is actually now twisted, and the optical axis is here and twisted along the radial coordinate in order to correct the dynamic phase unwanted modulation. And here are the four plates we were dealing with. And if we look closer, or is distributed in a transverse plane, the fabricated optical axis distribution. You have this for the uncorrected plate and this for the corrected plate. So here again, we see that this radial modulation of the optical axis distribution dictated by the actual dynamic phase that we have previously analyzed from the uncorrected plate to have a correction adapted and specifically adapted to the material used and to the optical fabrication of the material that we used. That gives the data, I would say, pretty close to the expected design plates. And here is the assessment of the plate that we fabricated. So the standard plate, the pure helical phase masks, the modulated retardance phase mask, but uncorrected regarding dynamic phase issues. And here we see that there is kind of aspheric wavefront modulation. We see that it's not really a mode, it's not shape invariant up to a stretch along the radial coordinate. However, if you go with the corrected version, here is the comparison between experiment and expectation for LG beam, here for L equal 1, and it's just, I would say, the picture is speaking by itself. So the mission is complete, and we are ready for quantitative assessment of the modality to finish the job properly. And for this, we need a tool. We need to have a model decomposition in a lab. So the principle is to recall that any field can be decomposed into modes, bases. This is LG, and we can simply define the weight of every mode by simply performing the appropriate field projection over the field that you want to analyze. And this is done in the lab in the following way. We have the field coming out of the plate. This is the one we want to address. And it is a reimage on a special light modulator, which imparts the phi star n function to the incident amplitude. And then we place a lens and look in the focal plane. And this is a Fourier transform by optical means. And this leads naturally to the to obtain at the focal plane on axis K0, and then we get by simply measuring the intensity on axis, we get access to the weight. And this has been implemented first by assessing what is the quality of the Gaussian beam, with the beam waist matching the design plate, and with this, which is here in the present case 250 micrometer. Extending this to all of the plates, what we see that there is an optimal, so again, the selection of the beam, output beam decomposition, which is different depending on the plates. And if we check the numbers, it well corresponds to the theoretical expectation from our approach, which scales in such a way with respect to the topological charge of the beam L. And here is the quantitative results. This is a summary, and we can appreciate the performance, the enhanced modal performance of comparing the uncorrected plates with respect to the standard ones and the corrected version. And of course, the gain is more appreciable when the charge is increasing, because as the charge is increasing, the L index is increasing, the radial distribution for pure helical phase mask is increasing. So this is where we are so far in this direction. We also developed a dielectric metasurface option by appropriately simulating the way the nano pillars made of silicon nitride could be used to shape the retardance profile the way we want. So here I show a piecewise design. There is a global, there are 13 meta units, and placing them appropriately, we can obtain, here we're obtaining the first dielectric modal metasurface. And this is the results regarding the propagation using metasurfaces. And this is what we get with our spin-orbic modal metasurface. We recognize at least a fair quality of and a fair improvement regarding modality once to be used or strategy. Still, there is a spin asymmetry because we are looking only one of the two circular polarization states, and the correction, the geometric phase correction for the dynamic phase issue is actually spin dependent and is operating only for one of the two circular polarization states. So far, this is one of the limitations we are working with now. And this leads me for the last 6 minutes on the emergence of new functionalities, this time done with Gonçalves, a colleague from CMS in France. And for that, we go with optical anisotropic media with a twist. To catch the picture, which is very generic one, take the situation of a well-known, I would say, optical material, which is birefringent, and whose optical axis can be easily shaped in space. This is nematics, nematic liquid crystals, where molecules are locally nearby to the neighbors. And there is a well-defined orientation here described by the vector n. Once you add some molecular chiral dopant to such a material, what you can get is helix. So you have a helical ordering of the optical axis. These are called the cholesteric liquid crystals, and they could be right-handed or left-handed, and the pitch is simply tuned by the appropriate amount of dopant and the choice of dopant. So we can easily obtain helically ordered anisotropic media. And this kind of media, in a very general way, be they liquid crystal or not, you obtain a very nice phenomena, which is called circular Bragg reflection, where the periodicity leads to interferential resonances, and where the chirality makes these resonances sensitive to the incident spin state. And what you get is helicity-dependent photonic band gap that you can use. You can use this reflectance, which is spectrally dependent, in order to have a selective circular Bragg reflection, and outdoor observation can make you observing such photonic band gap physics driven by spin states simply by looking at some beetles in nature. And the idea is to exploit this by seeing the connection between the usual spin orbit behavior and the way circular Bragg reflection operates. Indeed, the co-handed light matter configuration leads to full transmission up to a phase, up to dynamic phase constant factor, nothing is happening. However, in the contra-handed light matter interaction, what you get is the following. You have the reflected wave with the same helicity, and with a phase that depends on the way the helix is oriented along its axis, which means that we have the equivalent of, we have a reflective spin flipper using anisotropic materials, chiral materials. And this means that we have a reflective version of the spin orbit plate we were exploiting just before. So this has been highlighted a couple of years ago, and the idea is to exploit it towards the vortex beam shaping. And here is the example how to simply extend previously space variant anisotropic media to space variant chiral media, and to obtain vortex generation with frequency control over the photonic band gap, and some deterioration on the blue and red side of the band gap. The point here to appreciate is that there is no polarizers. We don't need to project by external means. It is self-contained in the Bragg structure of the system. If you go one step further and you shape in space the very value of the pitch, then you have a gradient pitch that increases the band gap. And then you can have a very large photonic band gap running over all the visible spectrum as shown here, and to have a really very broadband spin orbit vortex shaper. Still, they are not that modeled, but still there is a frequency asset now. and to recover the spin control wavefront reversal, which is the main asset of a spin orbit photonic elements. The idea is to get this Bragg reflection operating for both spin states, which is not the case using a single film of a chiral liquid crystal. So the idea is simply to place a mirror on the back of the structure, and due to a nice game of helicity preserving or helicity flipping between the usual reflection and the Bragg reflection, at the end of the day, you can have shaping of both spin states from a single structured plate of chiral and anisotropic media. And this is experimental demonstration of it, where on the right, you can appreciate that both spin states can be shaped as a vortex beam in a polychromatic manner without much pain. And this leads me to the two final slides, which is the way we encountered enhanced functionality from even more elaborated structuring of chiral anisotropic media, exploiting a non-singular biomimetic situation. The idea is to use this helically ordered anisotropic media and to place them in a box, so a slab in practice between air and glass, to place a layer of such a material and imparting two perpendicular boundary conditions for the molecular orientation. What you get at the end of the day is a self-organized polygonal texture, which mimics the one you can observe on the cuticle of beetles. And if you look closely to this one of the polygonal cell, this is what you get with polarization result imaging. You get an azimutally distributed optical axis with a space variance retardance. And I guess here you get my point, is that here we do obtain a model-like naturally occurring system, because we have azimuthal geometric phase shaping and we have space variant retardance. However, in this system, it's even more elaborated, because along the z coordinates, so perpendicular to this plane, there is a variation the way the helix is distributed in space in an umbilic-like manner. And this is what confers this topological charge 1 to these polygonal cells. And with a careful experiment of the structure, we can obtain the full distribution of the optical axis, which is topological charge 1, gradient pitch along the axis, plus radial modulation. If you construct the dielectric tensor, the 9 components of the dielectric tensor from out of this analysis, experimental analysis, then you can simulate the behavior of the system. And you can compare with experiments. And in that case, what we observe is that we have a spin-dependent vortex generation. However, in a forward direction. The Bragg reflection, circular Bragg reflection, only occurs here in the photonic bandgap. For all other places, you have vortex generation. And what we realized, and this is my last slide, is that if you place yourself in a situation where you have a Bragg reflection, this side of the sample being absolutely not structured, you have the usual Bragg reflection, and this is the output field. There is nothing. Okay, we check experimentally, there is nothing. But if you go from the other direction, then the left-handed circular polarization will enter, will see its polarization state change because there is birefringence. And then there is a Bragg reflection occurring in the bulk of the medium. And then the unconverted spin states will be self-filtered by the circular Bragg reflection. In that case, you get a self-filtered optical vortex generation by spin orbital means. And if I summarize this behavior, we actually obtain what we can call a spin orbit optical diode effect. The cartoon is just summarized here. And so this surprising spin orbit photonics functionality actually drives us to look more closely biological structures and we wish to continue in that direction and to unravel, I would say, unexpected functionality that could give us hints of how to engineer new optical elements for its performances. I thank you for your attention.
Thank you very much. Believe we have time for, we can have one question if there's anyone who wants to ask a question about this. While people think about that, I'll also ask if our next speaker is present.
Okay, thank you.
Thank you. The next speaker I have on the schedule is Professor Omatsu, if they're present. Ah, yes.
Okay. Yeah.
And thank you very much for that presentation, Professor Brasselet. And
Okay. Can I share my PowerPoint file?
hopefully you should be able to.
Can you see it?
Yep, we can see your screen. You just need to share up. And
Okay.
yeah, if you are ready to go.
Okay. Thank you very much for your kind introduction. My name is Takashi Omatsu, Chiba University in Japan. So now this time, unfortunately, I cannot visit the Ukraine. The visit to Ukraine is inhibited by the Japanese government. So the next time I definitely visit the Ukraine to discuss with you in person, definitely. I hope everything becomes settled very soon. Anyway, title of my talk, laser nano microfabrication using structured light. Okay, the beginning of my talk, I briefly acknowledge many collaborators thanks to the financial support, JSPS, Kakenhi, evolution of the color material science using helical light field, and JST Crest, innovative optics and photonics. Okay. Yeah, I don't want to talk about the detail of the optical vortex. Of course, optical vortex very familiar for you. Helical light field, the carry the OM, yeah, characterized by the quantum number topological charge L, come from the periodic boundary condition, and it exhibits annual intensity profile with the central dark core. Now, of course, we can assign the hardness of the optical vortex determined by the twisted direction of the helical wavefront, So the optical vortex is quite interesting, that we can drive the orbital motion of the droplet particle like that. Okay. So this must be the new freedom of the optical manipulation, definitely. And annual intensity profile that can improve the spatial resolution of the scanning fluorescence microscope. And topological charge, this must be the freedom of the telecommunication to increase the data capacity. So I want to focus on to the chirality of the structured light. Why chirality is interesting? We directly control the chirality of the structured matter. Okay? Now, because chirality is very universal, is very fundamental in the material science. For example, the asymmetric synthesis in chemistry, so that we always thinking about how to distinguish left-hand and right-hand chemical composites. This must be the very important topics in the chemistry. And the human body, the made of the amino acid, but mostly amino acid left hand. Why right-handed amino acid doesn't exist in nature? This must be the still mystery, homochirality. Of course, currently, the 2D material is very popular. At that moment, we were thinking about the chirality, helicity. And in the view of the optical science and photonics, metamaterial, left-handed matter exhibit negative refractive index, and optical vortex light field carry the orbital angular momentum and chirality and helicity. Anyway, chirality and helicity, very important in the material science and physical phenomena at that moment. We want to control the chirality of the structured matter by the helical light field. This must be our motivation. That we must back to the already 15 years ago. That we proposed one basic idea to control the chirality of the structured matter. We shine optical vortex on the material, material surface melted or softened can be considered as some micron cluster. At that moment, they will receive orbital angular momentum from the optical field, start to rotate clockwise and anti-clockwise direction. The laser field suspended. At that moment, material recrystallized, resolidificated on the surface of the matter to form the color structure. Normally, the color structure, some micron scale, just the position of the optical vortex. Yeah. This must be the very useful technology to fabricate a color structure. That because we don't have to utilize cryogenic atmosphere and vacuum chamber at all experiment can be performed in room temperature and atmosphere. So last decade, we have done so many demonstrations. Okay, quite successful. I briefly show you several demonstrations. Initially, we performed the experiment by using the tantalum, the metal. Okay, after that, move from the metal to the semiconductor silicon. And currently, we try to control the structure of the matter of the polymeric fiber, we inject laser beam inside the collagen. At that moment, we can fabricate such a fiber with twist, all material twist just by the position of the optical vortex onto the matter. And we also can control the helicity and the chirality of the structured matter just switching, twisted direction of the spherical wavefront. This must be the very interesting topics, Currently, we are working on isopolymer, So the metal and semiconductor, normally we must use a pulse laser, but as a polymer case, it exhibits photon radiation, a visible light, CW visible light is okay to form the color structure. At this moment, I want to focus on the polymer topics. As a polymer, the quite unique property, it exhibits quite unique property, photon radiation by the visible light illumination from trans phase to cis phase, So the shadable, the visible light coming to the matter, the cis phase and polymer become mostly dominant. At that moment, surface must be softened. They will receive the photon radiation pressure and photon-induced mass transport occur from the bright region to the dark region. Okay? At that moment, surface must be the default. So laser field suspended. At that moment, we can create some surface relief formation onto that polymer center. And generally speaking, a structure of the surface relief reflect a spatial distribution of the illuminated light. Okay? And as a polymer itself has some self-polarization, So structure of the surface relief is also reflect a polarization state of the optical field. But nobody thinking about, wavefront sensitive surface relief formation ever, Now we try to experiment by using the surface relief formation by using helical light field that already 5 or 6 years ago. I would like to show you beautiful demonstration. The orange color, this must be the isopolymer thin film. The thickness typically the 500 nanometer or something like that, We shine optical vortex, left-handed, right-handed. Our surface becomes softened as the polymer starts to rotate clockwise and anti-clockwise direction. Several seconds later, we can fabricate such a beautiful structure onto the isopolymer, So after that, we're thinking about further control the structure of the surface layer onto the isopolymer by changing topological charge of the light. Okay? Of course, we try to change laser power, exposure time, and wavelengths, and so on, so on, so on. But always the fabricated surface relief, just single helix. Even by using second order optical vortex, third order optical vortex, we can always fabricate single helix structure. Currently, this must be the collaborative project with Professor Okamoto in the Institute of Molecular Science. So that we combine the near field optics with optical vortices, Of course, we can make smaller the surface relief down to the, the 300 nanometer sub-wavelengths. But still, our structure is single helix. Okay? Back to the structure fabricated by optical vortex elimination. We found all structure is single helix, In the case of the twisted matter onto the metal, twisted metal material onto the silicon, twisted fiber formation inside collagen, and in the case of the isopolymers, well, the all structure must be single helix. This must be our question. We can fabricate a multi-helix structure. Yeah, is possible or not? At that moment, we're thinking about, new concept to fabricate such a multi-full helix structure. At that moment, material is isopolymer, but this technology must be universal to be applied to the all kind of the material, definitely. We're thinking about coherent superposition, orthogonal vortices. We want to say this is a hybrid OM state, left-handed, right-handed optical vortex, the coherent coupled with each other. We can generate such a petal-shaped structure, At that moment, that in the case of the topological charge plus minus one, the petal beam structure, with two petals, like the twin beam. If we increase the topological charge up to the 2 or 3, this hybrid OM mode, with the even number of the petal, the 4, 6, 8, or something. Yeah. Such a hybrid OM state doesn't carry chirality on OM. But if we try to add some spinning motion by using the station right modulator or chirp pulse amplification or something, that we can control the spinning motion with such a petal beam. At that moment, we can assign, the chirality of the hybrid OM mode determined by the direction of the spinning motion. And spinning motion of the petal beam also carry effective OM to the matter, We try to use such the petal beam, hybrid OM mode, with several petal. The basic concept is quite simple experiment. That we prepare the 532 nanometer green CW laser. Laser power is about 1 milliwatt, 2 milliwatt, something like that. Not so much high power. To control the wavefront of the laser beam, we utilize the spatial light modulator. The structured light focus onto the isopolymer thin film. The thickness is about 1 millimeter. The spot size typically couple micrometer. Effective numerical aperture objective length is around 0.4, 0.5, or something like that. We don't have to care the longitudinal electric field so much. So at that moment, we add spin angular momentum of the light. Yeah. By utilizing the quarter wave plates. Okay. So in the case of the simple vortex beam, that we can fabricate single kind of structure onto the polymer. But if we try to use a twin mode, spinning to the clockwise, this must be the very surprising that we can fabricate a beautiful structure, double arm structure. Of course, we can control the chirality of the structured matter, quickly. The shape very similar to the spiral galaxy. We want to say this is the galaxy surface layer, At that moment, we found the very interesting phenomenon, to fabricate such a galaxy-shaped surface layer, spinning direction must be same as direction of the circular polarized ray, namely the clockwise rotated spinning the twin mode with left-handed circular polarizer can fabricate such a beautiful structure. But if the circular polarizer polarization become opposite, okay, now we cannot fabricate such a the double arm structure anymore. This means the spinning motion of the hybrid OM, the carry effective OM, this effective OM interfere with the spin angular momentum of the circular polarized light, constructively interfere, destructively interfere. Okay, in fact, the linear polarized hybrid OM state, the intrinsic OM is zero, but the surface is slightly tilted. This must be the the spinning motion induced effective OM. Okay, this must be the very interesting mechanical motion of the structured light, coupled with the spin angular momentum of the polarization. Now we can fabricate freely double helix structure, quarter helix structure, six helix structure just by changing the topological charge of the light. Of course, we can also control the chirality, quickly by swapping the spinning motion direction and circular polarization direction, And we also can control the orientation direction of the such a structure quite freely, the very nice the technology, I think. At that moment, we can fabricate, the even order, the helical structure. So the odd number helical structure can be fabricated or not. This must be the just extension of the hybrid OM, namely the coherent superposed by the different order topological charge and the optical vortices. For example, minus L Lagrange Gaussian mode plus L plus ones, the Lagrange Gaussian mode coupled with each other, that we can create the hybrid OM state with 2L plus 1 petal, such the laser beam must be the spinning like that, at that moment we can create the beautiful color structure with the odd number of spiral arms. Anyway, by using the hybrid OM state, degenerated one or non-generated one, we can control a chirality of the structured matter. And we also can fabricate much flex helix structure freely, This must be the absolutely new freedom of the microfabrication, I think. So, generally speaking, the helical structure in the nature, just not only single helix structure, double helix structure, triple helix structure, quarter helix structure, such a structured matter must be used for the simulator of the biomaterial, definitely, We want to apply this technology to another material in the near future. At this moment, I want to change the topics, Currently, we try to utilize the optical vortex for the crystallization, okay? This must be a very simple idea. The laser beam tightly focuses onto the solution, including a molecule, The gradient force can trap aggregation of the molecule. At that moment, the nucleation occurs. This nuclei grow up to the crystal, that within a couple of minutes. The typical size of the crystal is about some millimeter scale. Just simply we focus laser beam inside solution. That is, this must be the very interesting technology to grab the crystal. So, generally speaking, molecule itself, achiral, doesn't carry chirality. But once crystallization occurs, crystal exhibits chirality. As such a molecule, there are so many molecules exist, Generally speaking, by using the circular polarized light as a light sources for the crystal goals, that we cannot control the chirality of the fabricated crystal. Normally, if we fabricate 100 crystal by using the circular polarized light, the fabricated crystal, the left hand, right hand, 50-50, we cannot control a crystal enantiomer excess anymore. At that moment, we want to utilize optical vortex for the license to the crystal growth. What happens? If we can control the chirality of the crystal, this technology can be extended to biology, pharmacy, medicine, many applications exist. This is true or not? Okay? We try to do that. At that moment, that we prepared sodium chloride water suspension. Sodium chloride is so a chiral, doesn't carry the chirality. Okay? And in order to accelerate nucleation, we add a small portion of the gold nanoparticle inside solution. A typical size is about 150 nanometer. Okay? We prepare the small cell, including the sodium chloride water suspension and gold nanoparticle like that, the figure A, We put on the this cell onto the microscope, inverse microscope. And we utilize light source, optical vortex 1 micron sources. Laser power is 1.31. The laser beam focus onto interface, the liquid and the air, What happened? I would like to show you a beautiful movie, okay? So we start to shine optical vortex inside cell. After a couple of minutes later, we trap the golden particle. After that, nucleation occurs. Okay, you can see some metastable crystal, at that moment. This metastable crystal is so achiral, doesn't carry any chirality. But we shine optical vortex, keep on doing much more. After that, the optical torque, act as the triggering of the transformation from the achiral crystal to chiral crystal, like that. Now we quickly measure the chirality of the fabricated crystal by using the polarization microscope. Okay, we fabricate total number of the 60 crystal. When we illuminate left-handed optical vortex with a topological charge L equal to, 80% of the fabricated crystal left hand. When we illuminate, shine right-handed optical vortex with a topological charge -2, now we can fabricate 47 crystal. This must be corresponding to 80% of the fabricated crystal right hand. Namely, the crystal enantiomer excess reach up to roughly 57-58%. 80% of the fabricated crystal can be controlled. Okay. So now is the topological charge just 2. Of course, we can increase the topological charge up to the infinite. That to combine with the perfect vortex technology, that we want to maintain the spatial form of the light field. At that moment, we can expect ultimate the crystal enantiomer excess. The close to the 100% definitely. We are preparing another experiment at this moment. Okay, our next topic that we want to control the photochemical reaction by the helical light field. This must be the fiber application. Okay. The laser beam tightly focus inside the QR region. At that moment, photopolymerization or photopolymeric matter exhibit relatively higher refractive index. They can confine the optical field inside. Now we can grow the fiber. This technology called self-written fiber formation. This must be the one kind of the self-focusing effect to balance the diffraction and the optical confinement inside fiber. We utilize optical vortex to fabricate fiber. What happened? Experimental setup quite simple. Now we use the 532 nanometer green laser, the pump source. We convert laser beam to the optical vortex by using spiral phase plate, and we want to make longer the confocal depths, the DOF, to generate Brasselet beam by using the axion length. The typical DOF roughly that couple millimeter inside. So, okay. What kind of the fiber can be fabricated? This was a very beautiful demonstration. Fabricated fiber are twisted. This is orbital angular momentum transfer effect. A fabricated fiber length reach up to the 1 centimeter. This is corresponding to the thickness of the cell. The fiber is so twisted. So still single arm structure, single helix fiber. Well, at this moment, we prepared another experiment in combination with the hybrid OM state. We can fabricate double helix structure, triple helix structure in the near future. Such a structure must be used for the simulator of the biomaterial. This must be the final topics. Currently, we are focusing on a printing technology based on the optical vortex. This must be the very interesting topics. Printing technology is very curious to develop the printed electronics, printed photonics devices, and so on. Mostly utilize inkjet printing, but inkjet printing has several limitations. High viscous material is not available. High density material is not available. Alternative method approach must be the laser for transfer. We pump a donor film by the optical field. Donor film is break into the many fragment fly away, launched onto the receiver substrate. We can freely pattern the 2D, 3D, all kind of the material. But generally speaking, we cannot control the spatial resolution when we make larger working distance between the donor and the receiver. How to overcome this drawback? We can get some idea from this just Japanese animation. Sniper hits a target. Okay? This bullet is spinning to stabilize straight front to attack the target. Same manner. If we transfer orbital angular momentum from the optical field to the droplet, we can stabilize the flight of the donor. The basic concept is quite simple. Just replace a conventional Gaussian beam by the optical vortex. Okay? I would like to show you a beautiful demonstration. So the donor, very high viscous material. The viscosity is about 4 pascal second, corresponding to the honey, The film thickness is about 20 micrometer, 30 micrometer. We pump this donor film by optical vortex pulse. Typically, pulse energy is about just 1 or 10 microjoule. Pulse duration is 2 nanoseconds. Okay, this is a collaboration project with Ricoh, a Japanese industry company. Okay, we pump the target by the optical vortex. Blister create. A chip of the blister can eject the jet. This jet is spinning, Now we can control the straight flight of the jet over 1 centimeter. Okay, that's quite long distance. Finally, Rayleigh Plateau instability occur. A single droplet eject from the chip of the jet. typical volume is about a picoliter level. This is corresponding, almost similar to that of the inkjet printing technology. Okay. We currently developed a prototype printed system. So that in order to extend this technology to the printed electronics, we utilize gold nanoparticle ink. Yeah, typical particle size is about 150 nanometer. So the typical the viscosity is about 100 millipascal or something. Okay. I would like to show you printed dot. In the case of the conventional Gaussian beam, the focus spot size on the donor film is about 40 micrometer, but a printed dot diameter 18 micrometer. Now, quite big. Okay, and we also can observe the many satellite debris, not so much beautiful circle dot. Okay, and just replace Gaussian beam by the optical vortex. Okay, the spot printed dot diameter itself. Yeah, the 45 micron, less than 45 micrometer. Okay. At that moment, numerical aperture of the objective lens, focusing lens, just 0.07, you know. And that we cannot observe any satellite debris. The very beautiful, the circle dot printed onto the receiver. I would like to show you some image of the printed dot. This must be quite surprising, you know. In the case of the Gaussian beam, the individual nanoparticle still exist. But in the case of the optical vortex pumping, the nanoparticle aggregated with each other. Now, this must be the sintering effect. Okay? Generally speaking, such the golden nanoparticle ink, of course, we can print many, draw the picture on the substrate. But in order to utilize the electronic devices, the sintering process is necessary. But in the case of the optical vortex pumping, without sintering, you know, electric conductivity is measured to be the 1.9 10 to minus 7 ohm meter. Of course, this value is one third of the bulk gold, but still okay. The printed as good as printed dot exhibit high electric conductivity, very beautiful. Of course, we can draw the picture like that. And when we increase numerical aperture much more, we can align a 15 micrometer dot. In the case of the inkjet printing, you know, the minimum size of the printed dot, normally the 20 micrometer, already beyond the inkjet technology. Okay, and I have another couple minutes.
Yes,
Okay.
you have a couple more minutes.
Okay, couple minutes. Now we can increase the further the numerical aperture objective lens, you know, the minimum size of the printed dot, 9 micrometer, absolutely overcome of the printed jet technology. And we also measured positional accuracy of the printed dot. Yeah, the red cross hatch is the target position, and green dot center of the printed dot, you know. In the case of the optical vortex pumping, you know, printed dot, absolutely track a target position, a typical the positional accuracy around 5 micrometer. This value is limited by positional accuracy of our two-dimensional the translator. You know, if we utilize the much expensive, much accurate the translator, definitely positional accuracy couple micrometer. Okay. Why such a phenomenon has happened? Yeah, this must be the high-speed camera image. In the case of the vortex beam, a blister itself is very small and shrink quickly. Such a rapid shrink of the blister that can induce negative inward cavitation pressure to confine the golden particle inside droplet. Yeah, you know, this must be a very important phenomenon, you know. And you can also observe some twist of the blister itself. This must be the orbital angular momentum transfer effect. Okay. We estimate the value of the cavitation pressure inside droplet in the case of the optical vortex, yeah, the laser irradiation after a couple of micrometer later, a couple of microsecond later, the cavitation pressure become negative. Inward pressure, the confined golden nanoparticle inside, across the pack, the nanoparticle must be the occur. So the printed dot exhibit very nice the electric conductivity without sintering effect. Okay. Anyway, optical vortex can twist the matter. But we can find out many fundamental material science. And of course, we can explore the innovative technology that, for example, printed the optical vortex in use for transfer technology. Such a technology must be useful toward advanced printed technology, absolutely, for the printed electronics, printed devices, printed photonics, printed biology, as well as. Yeah, currently we publish one paper from the ACS photonics. Yeah, we print maybe the glycerol droplet onto the substrate. This droplet, including the laser dye, individual droplet, the lasing as a whisper gallery mode. Such a technology must be used for printed photonics devices. Okay. Now recently we're thinking about some concept, evolution of the color material science using the helical light field. This material 5 years transformative research areas project in Japan. Okay. The total budget is about 10 million US dollars. Now we can explore the many directions. For example, the helical light field collect the nanoparticle into the molecule to create color structure. This must be the one kind of the very important research topics, color crystallization in chemistry. Another interesting topics that we can fabricate helical structures. This must be the work as a simulator of the biomaterial. We want to approach the biology, biotechnology, including the tissue engineering and so on, And vortex itself, very fundamental structure. In the solid state physics, we want to control the solid state, such a vortex structure on the surface of the matter freely by using the optical field. This must be the innovative technology in the solid state physics, definitely. Anyway, biology, the chemistry, physics, all topics must be included, that integrated inside this technology. And in this project, we always open the PhD candidate and postdoc. Thank you for your attention.
Thank you very much for a very interesting talk. We have a moment for a question or two. Does anybody have a question? Yes. Professor Mokhun, go ahead. Oh, your audio is a little distorted at the moment.
Yeah, I cannot understand what you want to say. I'm so sorry. Probably a communication issue, I think. Yeah.
Your audio is a bit distorted. Would you be able to just write your question in
please send
the
message
chat?
to me. Yeah, please send message to me. Much easy. Yeah, the probably internet connection network issue, I think. Yeah.
Yeah. So yeah, if you can, please feel free to add the question in the chat. And
no, I'm so sorry. Yeah, I'm so sorry.
Yeah, the audio is not audible right now.
Please write in chat.
Yeah, thank you.
Yeah. Anyway, anytime okay. Please send a message to me. Yeah. I send back. Yeah.
Okay, well, thank you. I guess we can move on to our final talk before the break.
Okay, thank you very much.
Yeah, thank you.
Thank you.
And our final presentation before the break is dampening of a speckle structure and low coherence optical field if the presenter is present.
Do you hear me?
Yes, we can hear you.
Do you see me or not?
Yes, we can see you.
Fine, fine. That's very good beginning of my talk. Well, so dear colleagues, greetings from Kiev. My talk is about speckles. So instead of usual problem, how to generate these optical vortices, I will speak on the opposite problem, how to kill them. And I will try to open my presentation. Do you see the picture?
Not yet.
Well, here.
Should be the share screen.
Now?
Not yet.
Wait a minute, please.
Yep.
So, demonstration.
Yeah, from the chat, they said Alt plus S should, here we go.
Yes. Fine.
Yep.
I am lucky. Yes. Well, so doesn't matter. So the task, our task is to damp a speckle structure in the coherent field. Everybody knows that the usual non-coherent field does not produce speckles, but a coherent one does. And the question is, in what extent must we spoil the coherence to damp the speckle structure? This question is actual in optics, for instance, in laser tomography, where speckles seriously degrades the image. This work is experimental one, even I can say empirical one. Starting the research, we had this idea in one hand, and what we had in another hand. In another hand, we have a so-called diode pumped solid state laser, which is familiar like a laser pointer. It's a very beautiful device. It's very small. On the right panel, you can see the actual size, about 2 or 3 millimeters of the cavity.
Could you be sure to advance your slide or move to the next slide? We still see the title.
Okay, could be this problem. Then I will go this way, sorry.
That will work. Thank you.
Yes, in this way it works. It's usual thing. Well, so in this picture, you see the diode pumped solid state laser, which is very small. And the cavity contains both active body. It's yttrium vanadium crystal doped by neodymium, and the KTP, which produce second harmonic generation. So it's kind of intracavity second harmonic generation. And this device is pumped by a laser diode. And in the output, we have two frequencies, actually, infrared radiation and the second harmonic radiation. Well, this type of lasers have has an interesting feature. Because of the very high density of light within this cavity, it can generate additional spectral lines. We found this occasionally about 10 years ago while working with this laser for excitation of the luminescence. Suddenly we observed an appearance of additional lines. And this radiation did not come from the sample. It just emerged from our laser. So we put a diffraction grating on the way of the laser output, and on the screen we observed 3 bright points. One corresponds to the fundamental frequency. One corresponds to the frequency to the wavelengths of 532 nanometers as usual one, and the second 537 nanometers, and the third 542 nanometers. What is the origin of these additional lines? We checked the fundamental frequency, and we detected that a part of the main radiation at 64 nanometers, there is one additional line which generates at 1084 nanometers. Well, then we found an original report on the subject that it's a common feature of this kind of yttrium vanadium lasers doped by iodine. However, its kind of oscillation is not stable, is not very good reproducible. To observe it more or less stable, we have to cool our laser to about 15 Celsius degrees. And we decided not to use it. And instead of cooling, we decided to heat our laser. And we succeeded, and we were surprised to observe an appearance of a new emission at 1066 nanometers when the temperature is 45 Celsius degrees. So at room temperature, we see the emission, which is blue line, normal emission, and 1064 nanometers, and the laser heated to 45 degrees generates 2 lines, and even we can tune a ratio between their intensities by the pump current of the laser. And in this second harmonic generation, as before, this bichromatic pump generates 3 lines. Why? First one is second harmonic of a fundamental frequency. The third one is the second harmonic of the new emission lines. And between them, there is some harmonic. Everything like in a handbook for the second harmonic generation. And this is very nice item because we noticeably changed the spectrum width, and therefore we first task was solved. We can control the spectrum width, we can decrease the temporal coherence of the radiation just with heating of our device, nothing else we have changed. Well, with this very useful tool, we can start with the second task. The second task is just to observe how it will influence on our speckle pattern. So this is a principal scheme of our experiment. We have a laser and the heater with them. The output, which contains both infrared frequency and infrared radiation and green radiation, is split by the beam splitter. A spectrometer controls the presence of one or two emission lines, and in the on the wave of the green radiation, we put a diffuser. This diffuser is a thin glass ground glass plate, which makes about 45 degrees in space of scattering with a speckle structure, which we observed at the focal plane of the lens, so in the far field. In this scheme, we detected both this speckle structure at the room temperature, when our emission is a single line, and this picture where we heat the laser to 45 degrees, and we have bichromatic in infrared and trichromatic in green radiation. And what we had observed, how do you think? We observed no difference. So we changed the coherence, we changed the width of the spectrum, but in our picture and CCD, no reasonable changes, nothing. It took 1 day to understand the issue. And now I will give an explanation just in 2 minutes. Please have a look what is happening. We have a laser beam with a transversal dimension d illuminating the diffuser. This diffuser in the far field produces speckle pattern. What is the scattering? The scattering is just a diffraction. It's a diffraction of the partial phase gratings within on the surface of this glass. So directly to the same direction as the illuminating beam, both wavelengths lambda and lambda plus delta lambda, which are mutually not coherent, they produce practically the same speckle picture. And the overlapping of these pictures just gives arithmetically addition of the intensity. So only the total intensity could change this, but not the structure. However, if you look at some definite angle theta, so the diffraction of these two wavelengths, even they are very close, will occur at a little bit different directions. And the pictures which are in form identical, they will be shifted a little. They will shift it a little on dependence on the angle theta. And on the next slide, I will show you the very simple calculations. Look, we have a partial gradient with a period lambda. And the diffraction law dictates that the sine theta will be the ratio of the wavelengths and this period. With the variation of the wavelengths, we have some angular deviation, which is written as proportional to the wavelength deviation and the tangents of the angle. Well, with a dimension of the illuminating beam d, this speckle angular dimension in the far field is just lambda divided on d. Could be some coefficient, but this is not important in our case. It's lambda divided on d. So we must shift in angular coordinate our speckle pictures exactly as to the value which is the same order as the speckle angular dimension. I believe that it's very clear. It's very simple. And the result is that we must have the tangents of the angle larger than written in red color. For our particular variation of the wavelengths, and the wavelengths which is corresponds to the our experiment, we have estimation of about 20 degrees, just very reasonable value, 20 degrees. In accordance with these calculations, we modified a little bit our experimental scheme. We put an opening at the angle with respect to the axis about 35 degrees. The same lens, which is of focal distance 85 centimeters, produce far field and at the focal plane, we put the CCD camera and the computer of the example is shown here. Then okay.
Did we lose our speaker at the moment? We'll give him a moment to see if he can reconnect. If anyone is able to contact Professor Vasnetsov, please let him know. Sometimes people are not aware when they lose their connection right away. We can give a moment.
We are waiting 1 minute.
Yep.
If he cannot connect, we have a break.
Okay.
There was a question from Mokhun in chat.
Yes. I was going to mention that for Professor Omatsu, there's a question in the chat from Professor Mokhun, if you have a moment to look at it.
Do you listen to me now?
Oh, yes, we can hear you.
Yes, yes, okay, that's fine.
I repeat my questions to the previous reporter. What can you say about the absorption of the operation medium and your results? And the second one, have you some dependence of the optical properties of operation objects and your results? Two questions.
Professor Omatsu.
Yeah, if he hasn't stepped away.
He's absent, yes.
He's absent.
Okay, so I guess we should take a break. I think
some little comment for the report of Misha Vasnetsov. Such speckle patterns may be obtained even for absolutely uncoherent case. And the speed of decreasing of contrast of such patterns may be used for the measuring of coherence of the beam. Thank you.
oh, thank you.
Thank you. We have a break now.
Yes.
Okay.
Yep.
Yes.
We have a...
And we use. Thank you very much. And we use the same link on the second part of this session, and that could be Mokhun, the next part. Okay.
Yes. And if Professor Vasnetsov gets back on by the time that I'm presenting, I'm perfectly happy to give him a few minutes to finish his presentation. Otherwise, we'll see you all in a few minutes.
Okay, thank you. We have a break and start at 11 o'clock.
Yep.
Thank you.
Like many people have already said, I hope to join in person in the next meeting. So I'm going to talk about the theory and experiment of an optical Hilbert's hotel, which is a topic that's been kind of entertaining me for a number of years. And I'll talk about kind of old stuff and more recent developments. And one thing I like to say about it is we know that infinite sets have very well-defined mathematical properties going back to the 1880s, but you can ask yourself if do infinite sets have any role in the real world calculations? And in recent years, I kind of came up with an unofficial mathematics saying that no matter how weird it is, all mathematics eventually finds application in technology or nature. And I could think of things like number theory, where it seems very abstract to talk about prime numbers, but nevertheless, they turn out to be very important in cryptography. And it's now been recognized that the mathematics of infinity appears in vortices of light beams in several ways. The discrete nature of optical vortices gives us an opportunity to kind of take a peek at some interesting and infinite mathematics. Now, I won't dwell too much on properties of vortex beams. We've already seen a lot of them. The only thing I will draw your attention to, looking at the usual Gauss pictures, is that the vortices are points in the cross-section of a beam where all the phase colors come together. And if the phase increases in a counterclockwise direction, we've got a positive vortex. If it decreases, we've got a negative vortex. And we know that if we're talking about monochromatic fields, that the phase must increase or decrease by this integer multiple of 2 pi, which we call a topological charge. And the topological charge of a vortex is a generally conserved quantity in wave fields. And when I say generally conserved, in the earlier days of singular optics, it was sort of left a little fuzzy that there were some exceptions to topological charge conservation. Because in general, you expect to see that vortices are typically created or annihilated only in pairs of opposite charge. You need a +1 and a -1 to come together to annihilate, or to be created, you need a +1 and -1 to appear together. And this stability and discreteness of topological charge in a vortices has led many, including me, to suggest using them as information carriers in optical applications. But that raises a natural question of, if vortices are only created in pairs, how are vortex beams created themselves, which have a non-zero topological charge? Well, one way you can imagine this happens, and you can see this in a number of situations, is you can lose topological charge at the boundary of the system, at the boundary of an aperture or at an infinite distance away from the center of the region. However, the other case is in systems of fractional topological charge. You get this really interesting relationship to the mathematics of infinity. Now, the traditional method for generating an optical vortex beam is you transmit a plane wave or a Gaussian beam through a spiral phase plate. And if you design that spiral phase plate to have an optical thickness, which is an integer number of wavelengths, the vortex beam of topological charge M will be generated. But it was back in 2004 that Professor Berry first looked at the fractional case and asked, what would you see if you have a spiral phase plate with that creates a fractional effective charge, where alpha could be integer, fractional, or any value you like. And this was followed up by some experiments around the same time by Li Qiao and Paget, which I'll discuss here. And the math, I credit Professor Berry for all of this, that he was the first one to originally say, well, you can figure out what happens when you transmit through a fractional spiral phase plate by just expanding that fractional phase that the fractional plate imposes in a Fourier series, an azimuthal Fourier series. And you can calculate, if you assume you've got a plane wave going through the system, you can calculate analytically the field of any integer vortex going through a spiral phase plate. And you can therefore figure out the total transmitted field of a fractional phase plate as contributions from a collection of integer plates. Whoop. And a picture that I like to use, you can kind of numerically calculate what happens to the topological charge as you increase alpha. Theoretically, we can do this trivially. Experimentally, it's another issue, but which we'll get to. But you find that the topological charge jumps by integer values when you hit these half-integer spiral phase steps. And that, again, seems to be a violation of topological charge conservation. We're suddenly just seeing a change without any obvious creation or annihilation process to explain it. And here again, you can see, here is the illustration of the phase in the vicinity of the origin. And we can see what happens as we increase this fractional charge of the plate through the value 4.5. And so we start with, for instance, at alpha equals 4.4, we've got 4 charges that were originally present. But we also start to see pair creation. And as we increase alpha closer and closer to 4.5, we see more and more pairs created, stretching off essentially to infinity in the plane wave case. And the white and the black pairs are labeled as white and black to illustrate which nearest neighbors were created with which other opposite charge. And so at 4.5, you can show you get an infinite number of pairs. And as you go above alpha equals 4.5, they start to annihilate from infinity inwards. And the key is that they annihilate not with the original vortex they were created with, but with their next rightmost neighbor. So here we can see now we've got a white and a black charge by themselves at 4.55. And finally, that annihilation results in a single extra unbalanced charge, which as alpha goes to 5, the 5 vortices, positive vortices, now coalesce into a single vortex beam. And this was the process that I kind of dawned on me a few years ago was very related to the mathematics of infinity. And to give you a little background, back in the 1880s, George Cantor asked, can we measure the size of infinity? A lot of us, including myself, as kids, we wondered, what's the value of infinity plus 1? Are all infinities the same size, or are some infinities bigger than others? And Cantor was able to introduce the theory of transfinite numbers and argued that in many cases, you can quantify, well, pretty much all cases, you can quantify the sizes of infinities and describe some infinities as bigger than others. And the way that Cantor argued this is by using the method of one-to-one correspondence. Normally, if you think about comparing the size of two stacks of finite objects, like I used M&M candies here as an example, the normal way you might think of counting or comparing which stack is larger is just by counting each stack and then comparing the numbers. But that doesn't work with infinite sets because we can't sit here and count to infinity. But you can do a one-to-one correspondence. You can line up the candies from each stack and see which stack has an unbalanced set of candy or M&Ms. So if you line them up one-to-one, and you can do that, a perfect one-to-one correspondence, the two sets are the same size. If you end up with unbalanced candies in one set or the other, you know that one set is bigger than the other. And this can be done for infinite sets as well as finite sets. So one-to-one correspondence allows us to compare the sizes of infinite sets. And Cantor showed that there are some infinities that are bigger than others, but he also showed that any pair of countably infinite sets are of the same size. So for instance, if you take the counting numbers, n equals 1 and up, if you add an extra element to that set, which I call A, you can still make a one-to-one correspondence because it goes on to infinity. So we can match A to 1, 1 to 2, 2 to 3, and so forth. And this is kind of like if you're a kid like me and you're talking about infinity, you say, hey, infinity plus 1 equals infinity, at least in this case. And similarly, the even numbers, the set of all even numbers is mathematically the same size as the counting numbers themselves, because you can make that one-to-one correspondence again. So you can say infinity plus infinity equals infinity, or infinity times 2 equals infinity. Now, where this starts to circle back to the example that we showed is that in 1924, David Hilbert, a famous mathematician, tried to point out how strange this infinite mathematics is. And he used the example of a hotel. And he said, imagine you've got a hotel where there's an countably infinite number of rooms, 1, 2, 3, 4, 5, out to infinity, and that all of those rooms are occupied. So the hotel has no vacancies. But you can always make a vacancy by having every occupant move one room up. And because there's an infinite number of rooms, every guest can do that. And you can always make an extra room. And you can repeat this process indefinitely. So Hilbert's hotel is simultaneously fully occupied, but also has infinite number of vacancies. And this is just summarizing that observation again. We can create one new vacancy by having people move one room up. We can have M new vacancies by having everybody move M rooms up. Or we can make a countably infinite number of new vacancies by having guests move to a multiplicative room, which means this hotel has no vacancies and an infinite number of vacancies at the same time, which is the point that Hilbert was making, is just that infinite mathematics is weird and it doesn't follow our common sense rules. So you would expect that you would not see this sort of mathematics appear in a physical system. But in fact, we can really say that this example that Barry first outlined back in 2004 really shows us Hilbert's hotel, that if we label the positive charges as rooms and the negative charges as guests, we can interpret the creation of these infinite vortex pairs as all the guests stepping out of their rooms. And then after we get past 4.5, all of the guests move one room up. That's the annihilation process, which leaves us with one extra room. And this kind of blew my mind the first time I recognized this. And so I decided it was worth mentioning and writing a paper about it, which came out in 2016. And one thing I like to note about this is you can also understand what happens, why we can create topological charge and violate topological charge conservation by thinking about it thinking about the sum of all the charges at that half integer topological value. Because at alpha equals 4.5, we're adding together an infinite sum of +1 and -1 topological charges of all the vortices in the system. But that's a non-convergent infinite series, +1, -1, +1, -1. You can, in fact, get pretty much any value you want out of this. For example, it depends on just how we group our sums. If we group together the first two terms and then every pair after that, we could argue that the sum is 0. If we leave the first charge and then group every pair after that, we can say the sum is equal to 1. And so part of the reason we can argue that the topological charge conservation is violated for this example is because we've got a singularity of topological charge. The topological charge itself is undefined for that half integer case. Now, one thing I'll mention, just a little background. When I first noticed this, I first happened to notice this Hilbert hotel connection because I was working on my singular optics book and I was studying Barry's example. And then I also had written some blog posts on the mathematics of infinity not long before that. And so infinite sets were very much on my mind. And then I wasn't sure whether it was worth publishing just that observation of sort of this connection to infinite sets. But I happened to be talking to a colleague at a Frontiers in Optics meeting who said, oh, we just showed Hilbert's hotel in a different way. And that kind of motivated me to expand upon my thinking and publish the results. And this other type of optical Hilbert's hotel that also appears in vortex systems comes from the way that we can encode and decode vortex beams. There's a geometric transformation we can do to basically demultiplex a bunch of vortex beams that are on top of each other. And that's by doing a geometric transformation from a log polar transformation. We can take an azimuthal phase and we can geometrically transform it into a linear phase. And that basically results, that linear phase becomes a tilt in a detector plane, and then different orders of the vortex become different tilts at different positions. And this was first done in 2010. And in 2013, however, some authors recognized that if you used basically a diffractive phase fan out grating, so you take that tilt and you basically kind of multiply it, what you end up doing is you take your original system, which had these different OAM states that were slightly overlapping in the image plane, and you can, by creating this grating effect, you can cause them to separate out. And they pointed out that basically you're multiplying the topological charge of each of the vortices by some integer value, which causes them to be spaced out more. And then in 2015, some of the same authors looked at this and said, well, that process is really equivalent to a multiplicative Hilbert's hotel. We're saying you're basically mapping the mode M to the mode 3m. So it acts as a modal version of this multiplicative Hilbert's hotel, where guest 1 goes to room 3, guest 2 goes to room 6, guest 3 goes to room 9, and so forth. And they referred to it as a quantum Hilbert hotel because they were thinking of it in terms of quantum mode, but you can think of this pretty much as classical modes as well. So this motivated me because other people were getting attention for pointing out a Hilbert hotel example to show that, yeah, we actually can see a Hilbert hotel-like effect in very different ways. But I wanted to go further than the example that Barry and colleagues had presented. And I pointed out that we can extend that original single ramp spiral phase plate and create an n-fold symmetric spiral plate. And when we make an n-fold plate, we can actually create multiple infinite chains of vortices simultaneously. And we can have the topological charge jump by in principle, any amount we want. In this case, I simulated a 5-fold plate and said, you can get the charge to jump by 5 over a very short change of your spiral phase plate ramp value. And in fact, you can go more complicated than this. In recent years, I showed if you make your plate non-symmetric and you make multiple ramps with different heights, you can pretty much get the topological charge to jump in any pattern you want as alpha increases. Now, one thing I should stress, and I try and stress this anytime I talk about this, of course, in none of these examples do we ever see an infinite number of objects. In this fractional phase plate Hilbert's hotel, we never see an infinite number of singularities because they stretch off infinitely in space in the transverse plane, and we're always working with a finite beam, and so you're always going to lose sight or lose track of your singularities in the darkness at the edges of the beam. And in the quantum Hilbert's hotel, you're never going to be able to measure modes of arbitrarily high order, and your system's probably going to have a limit of how high of a topological charge you can multiply before your system resolution kind of breaks down. So when I talk about seeing infinite mathematics in optical systems, I refer to it as the signature of infinite mathematics. You're kind of seeing you're kind of seeing a hint of what would happen if your system was allowed to go in principle to infinity. And it's worth noting that the first experimental observations of this, as I mentioned, were done by Lee Chow and Paget, where they saw this infinite vortex chain and looked at a number of integer values and did both the simulations and the experiments to see that they were in agreement. Now, to go a little further, so after looking at a Hilbert hotel in optical singularities of phase, I was curious as to whether we could do something similar in the polarization case and what you would expect, whether anything would be different in the polarization case. And in fact, there are some interesting differences that can arise. And the reason that they can be different is that the topological properties of a polarization singularity are different from the topological properties of a phase singularity. So polarization singularities also exist. And a polarization singularity, the type that we'll be mentioning are what are usually called C points, or points of circular polarization. At a point of circular polarization, the polarization ellipse orientation is undefined. And so we could say that the orientation is a singularity there. And you also get a conserved quantity called the topological index. And the topological index is the number of times that the major axis of the polarization ellipse rotates around the singularity when following a counterclockwise path. And the topological index has to be half integer value. because the polarization ellipse is rotationally symmetric when you rotate it 180 degrees, a half integer index is sufficient. And so we have a +1/2, which is usually called a lemon. A -1/2 is what's usually called a star. And a non-typical, non-generic case, but one that's very often used and very important, is radial polarization, which has a topological index of 1. Now, so theoretically, I was interested in studying what happens if we make a fractional polarization element and look at what happens to the polarization singularities as we increase our fractional element. So I started with radial polarization, and I said, okay, radially polarized light can be described very simply. And let's just add a fractional alpha into that definition. And my original hypothesis was that as alpha increases, we should expect to, when alpha reaches 1/2, you might expect that you would first get a single lemon through a process of this sort of infinite Hilbert hotel, and then you would expect a second lemon to appear. And a little bit of notational change. It's very nice to be able to draw pictures of all the polarization ellipses, but it's very hard to see what's going on when you do. So we can also use just color to describe the orientation of the polarization ellipse as well. So the color just represents the angle of orientation. And then you get a picture that looked very much like our phase singularity picture again, and we can spot the singular points by all the colors coming together. Well, the polarization Hilbert's hotel, the interesting thing is as alpha goes to 1/2, you don't get just one pair of singularities appearing, you get two pairs at the same time. You get lemons and stars, two pairs created together. And as you get to 1/2 alpha, you get two infinite chains of singularities. And as you go above, those two chains simultaneously start to annihilate with their nearest neighbors back until you get basically two positive singularities, so two lemons. So it ends up acting like Hilbert's hotel again, but with everyone shifting two rooms instead of one room at the same time. And that's one of the variations that happens when we consider polarization instead of phase for this Hilbert hotel mechanism. Now, why does that happen? Why doesn't it do what I predicted it would do? Well, our fractional polarization element, when alpha equals 1/2, we end up with a phase jump at phi equals 0, at the azimuthal angle phi equals 0. And so that causes us to have the singularities appear as they do. If we want to see that original process where as we increase alpha, we first get a lemon and then we get two lemons or radial polarization, we have to modify our electric field to kind of counter that phase jump that happened. We had an extra phase term. And then, in fact, when you do that, you find that the pair production that happens, you get just a single lemon created when alpha is 0.5. And then when you get to alpha equals 2 for this particular realization, you get effectively radial polarization, what I've called a lemon-flavored Hilbert hotel. And so both of these involve getting a radially polarized field through a continuous change in the parameter of the optical element being used, but they undergo different topological processes to get there, which I think is very interesting, and I want to build on this further with future research. Now, most recently, I've noted that there was this early experimental work in 2004 that showed sort of the basic theoretical work of Berry held up. But after I published this paper in 2016, kind of connecting it to this Hilbert hotel mechanism, a number of researchers wanted to look and study this process in more detail. One experimental result came out in 2022. At the time that that paper came out, I was already working with some colleagues at the Physical Research Laboratory in India to do a different version of the experiment. And this is the experimental setup that was used. And the idea that was used here was to use a fixed spiral phase plate, but instead of trying, so the 2022 experiment used basically a deformable mirror to create the fractional step. Here, instead, we used a fixed spiral phase plate and used a supercontinuum laser. By changing the frequency of the laser, you're basically changing the fractional order of the phase plate. And the nice thing about this is that this was not only a nice, elegant experimental realization of the Hilbert Hotel using phase and using scalar beams, but also by creating using a beam splitter and a delay line, a polarizing beam splitter in particular, we were able to create fractional polarization states as well, and look at the first example of seeing this Hilbert Hotel effect in the polarization case. Now, to show you just some of the experimental and theoretical results, this is for the phase case. You've got your interference fringes, and then those interference fringes are interpreted in terms of a phase distribution. And in fact, for being a supercontinuum laser, they were able to change the wavelength on a very fine scale in order to really see this production and creation and annihilation of singularities in the process. And one of my students did a theoretical comparison using the experimental parameters, and we were delighted to see that it worked very, very well, and there weren't any unexpected experimental wrinkles that caused a difference. And I was also very excited to see the polarization case taken on. I had done the theory of the polarization case with a student a few years earlier, and had never seen anybody take it up and try and see the polarization of Hilbert's Hotel. Oh, and I should also mention that you may notice there are two lines of singularities being created as the frequency or wavelength is changed. That's because this was a 2-ramp spiral phase plate. So this was the first time that somebody also verified the prediction that using a multi-ramp spiral phase plate would give you multiple chains of singularities at once. But in the polarization case, they were also able to confirm that you get, and this is analogous to in essence, to the lemon type singularity. You get a single chain along 2 lines. And again, it matched really well with the theory. Now, I've actually gone faster than I needed to, but that'll give me some time for questions or for us to fill in a little bit of extra stuff at the end. There are other systems that have some interesting behavior similar to this. In fact, my colleague at the Physical Research Laboratory originally reached out to me. The original project we started working on involved Poincare-Bessel beams. A Poincare-Bessel beam is essentially a superposition of Bessel beams of different orders with orthogonal polarization states, which end up having the properties of Bessel beams, but also have polarization singularities present. Now, most people have focused on Poincare Bessel beams where you create them in a circular polarization basis. In our case, my colleagues created Poincare Bessel beams using linear polarization states, and they found that you in fact get a beam that automatically has an in principle infinite number of lemons and stars, actually lemons on the left, stars on the right, infinite chains automatically that stay on propagation. And one thing we've been trying to study is what happens if you block an odd number of singularities in the middle. We know that Bessel beams are self-healing, so we know that we expect that after propagation a sufficient distance, we should get back all our original singularities. But how do those singularities reappear? And it turns out that the process is surprisingly complicated and hard to figure out what exactly is going on, which is why our paper on the Hilbert Hotel came out before this paper. But we've submitted for publication some preliminary experimental and theoretical results on self-healing of these Poincare Bessel beams with this linear basis. And we'll be doing more analysis of this in the future, which shows some very interesting and complicated evolution. Overall, I'd like to say there are we have systems with singularities. Phasor polarization can reveal great surprises, such as this Hilbert Hotel basically shows you a mechanism that mimics or looks like the transfinite mathematics of Hilbert's Hotel in the creation and annihilation of vortices or other singularities. And again, I stress, because I don't want anyone getting angry at me for saying we're viewing infinity, that in realistic systems, these infinities are always sort of hidden or truncated in some way or another. And personally, I find it interesting in seeing what different ways these infinities can be hidden in these realistic systems. But the signature of the infinite mathematics is clearly seen in these systems. And both vortex systems and polarization systems can show these effects. And I'm interested in looking in the future whether we can use these insights to develop better optical elements. And thank you very much. I will stop there.
Thank you very much for the nice talk. And now questions and comments.
I was almost certain Mark would have some sort of question.
Yes, please.
Hi, Greg. Thanks. There's a really nice collection of ideas all coming together in an infinite way. So I was interested in the comments that you made about how you sort of lose the infinity in the edges of the dark beam, which is the sort of experimentalist way out of it. But I know that the mathematics of Hilbert's Hotel, people have said, you could say, for example, get the hotel to fill a finite volume if each floor took was half the height of the previous floor, and so on. And so I was wondering whether there may be an analog of that you could sort of compress your infinite number of singularities in, say, a dark patch like you were just talking about for your Bessel beam, and then you could sort of keep on pulling them out one by one. Is that something that might work?
You are very astute, because that picture that I showed of the Poincare Bessel beam, I think that's actually what's going on there. There is this picture in that dark area, you see this sort of set of rings in there, which there are a large number of singularities in there. And I'm pretty confident at this point that what you're seeing, roughly speaking, though I need to quantify this better, is that you've got basically a continuous area singularity that you start with, that in the extreme near field after that dark patch kind of breaks into sort of an infinitely dense set of singularities that then spread out and annihilate.
So it'd be quite interesting to actually see what happens along the boundary condition there, because it's probably going to be some sort of like an essential singularity in complex analysis where anything can happen.
Yeah, I'm currently working on the kind of the an analytic way to sort this out. Like the pictures that I showed when we first started this, I had no idea how to do any of this analytically, so everything was done computationally, which was great because it agreed with the experimental work really well. But in the early experiments, we were focused entirely on the singularities outside the dark patch and how everything came back together. And then I started saying, well, something weird's happening inside that dark region. And we also see that in the experiments. You can also see those sort of rings and everything else and those singularities in there. So now I've actually pretty well done some analytic work in the near region there to see what's happening. Though I'm still having arguments with my student about whether I've done the math right or he has.
I look forward to seeing what you come up with in the next paper. Thank you.
Thank you. Great question.
Questions? I have a little practical question. What do you think about the creation of spiral plates from the electro-optic materials? And in this case, we can permanently change the refractive index and correspondingly permanently see the changes in situations, maybe?
Yeah, I mean that could be another very interesting way to see the same sort of mechanism. If I understand correctly, you're saying let's change the actual refractive index of the spiral plate, which would be a nice complement to the other two methods that I mentioned, because as I've mentioned, the first experiment that the 2022 experiment, they changed the ramp height to get the change in order. Then the experiment that my colleagues and I collaborated on, they changed the wavelength, and that naturally leaves the refractive index as a final choice.
Thank you. Thank you.
Thank you.
Somebody have questions? No. Okay, thank you again. And now the report of Professor Kumar from India, machine learning meets singular optics. Please.
Hello.
Oh, yes.
Am I audible?
Yeah.
Yeah, thank you. Thank you. I'll share my screen.
Always okay.
Yeah. Can you see my screen?
Yeah.
Okay. Yeah. Okay. So once again.
Could you see if you can switch between the presentation view and speaker view? We're seeing both your.
Sorry. Okay.
I think under display settings, it might be.
Yeah. I agree. Totally agree. But how to switch the screen?
Yes, swap presenter and slideshow.
Yeah. Now it's better?
Yeah.
That's perfect.
It's okay.
Yeah, thank you for the help. Yeah, so here it is good afternoon. So it is 2 o'clock in the afternoon. So a very good afternoon from India, and I suppose there it will be a morning time. So a good morning to all. So yeah, so first of all, thanks for giving me this opportunity. And yeah, so I will be talking about a little bit on my work, what I have started working after joining as a faculty. Previously, I have started this work as I can say some sort of I was fortunate to work in the field of singular optics, and then obviously I have to grow as time grow. And another thing is that because of the COVID, I started working and exploring a new field of machine learning. So I got a lot of time to explore, and then let's see if I can able to unify it with the field of singular optics or whatever knowledge I have gained so far. Okay, so with this kind of a preliminary remark, so I have given the title as machine learning meets singular optics, but that is a very broad topic. So here I will be focusing on the speckle-based OM demultiplexing. Basically by using of the machine learning techniques. We know there are a lot of OM demultiplexing techniques are there, but here we will be focusing on machine learning, and then we'll see obviously what are the advantages it has, and obviously it has some disadvantages as well. So this is the organization of the talk. So let me first put into the perspective. So I will be channelizing, I will be, I can say, giving a face to my talk, which is basically the optical communication using the
We didn't listen to you.
Yes, we've lost your audio.
Maybe some problems with communication.
Hello.
Oh.
I suppose, am I audible now? Hello?
It's
Yes.
okay now. Yes.
Okay, I'll switch to my speaker phone rather than the headphone. It's creating trouble. Hello. Hello.
Yeah, I think we can hear you.
We did not listen.
Yeah. So thanks. Just please interrupt me if you're not able to listen, because maybe I can't able to hear you guys. So please interrupt me if you can able to hear me, or if I'm not able to hear you, then it will be waste of both of us time. Thank
Okay.
you. Thank you. Now it's perfect, I suppose, because now I came to my speaker, PC speaker phone. So, okay, as I was talking about, let me put the full screen mode. So it's all fine, full screen?
Whoop, switch the display setting again.
Okay. Yes, now it's fine?
Yep.
Okay. So as I said, I will be putting in a proper context of projecting my problem into the today's demand, where we need where we are living in the era of the exponential mobile data requirement, and then that can be solved based on the space division multiplexing. And then we will try to see how the AI has revolutionized the space division multiplexing, which is little difficult to achieve. And then it also has some, I can say, drawback that we have overcome by proposing the speckle-based demultiplexing, and then that demultiplexing we have applied to the OM shift key and newly proposed non-line of sight optical communication using the structure light, which is hard to achieve. As I was saying that if you see the graph, so today's data requirement is keep on growing exponentially. And then in order to meet these demands, the answer to is that space division multiplexing, because all the other multiplexing techniques has been exhausted. And as you can see in this graph, that without the use of the space division multiplexing, today's current data requirement or maybe the future's data requirement cannot be met. So space division multiplexing is the next upcoming big things. So how to achieve the space division multiplexing, or just to little bit know about space division multiplexing, I'll just tell you regarding the different multiplexing techniques. So far we have it based on the whatever the degree of freedom electromagnetic field has. So as you can see, these expressions of the electromagnetic field, these electromagnetic fields has various degrees of freedoms. First is the polarization, so which can be used as polarization multiplexing. There will be like amplitude, so I can have amplitude as well as the phase demultiplexing, wavelength multiplexing, frequency as well. And then obviously the thing which is left over is nothing but the space path or the special profile of that mode. So that I can utilize by having a multi-core fiber, or I can utilize by making the special profile of the mode. And within the special profile of the mode, obviously they can be a scalar mode and they can be a vector mode as well. So here we will be talking about only the scalar mode having the OM.
So just to have an introduction of the OM, I don't have to give it to you guys because this singular optics is well known nowadays. So the OM automatically, the Allen has already proved in 1922 that it can be solutions of the Brasselet equations, and the mode which get it is Lagarikos mode, and those mode can be associated with the orbital angular momentums. And these are the, first of all, the basic beams, which is we called as a Lagarikos beam, which is containing the orbital angular momentum, and this term I raised to L5 is associated with the helical phase term, as a result of which this Lagarikos beam will have orbital angular momentum. And these are the few, I can say, images of some of the modes, Lagarikos mode, and the corresponding phases. There are other families of beam which is does not have orbital angular momentum. They are called as Hermite-Gauss beams, which also I will be making use of to implement my OM shift scheme. So let's start with the demultiplexing techniques traditionally. So traditionally, there are two major class of techniques which are available, along with some of the technique which has last speaker has already highlighted it. So in the interference-based technique, you have a reference beam, and that will be interfering with the corresponding OM beam. And then depending on the fork pattern, I can make which kind of OM beam it is. And on the contrary, you have a diffraction-based technique where you have some sort of aperture, and the OM beam is allowed to pass through that aperture. And by looking at the far field pattern of that field far field pattern of that beam due to the diffraction of that particular aperture, and then based on the far field pattern, I can make a conclusion what kind of beam it is, or what could be the charge of the OM mode. So in this case, they have used a triangular aperture, and then obviously depending on the charges in the far field, we get the different, we get number of modes, number of, I can say, maximas is keep on changing on the edges of the pattern. So, but as I said, these are the major class of it, and then these kind of technique generally heavily relies on the alignment issues. So as an example, suppose if I have to apply this kind of technique in our day-to-day life, so in case of optical communication, then beam wandering is one of the biggest issue, where if from the receiver to the transmitter, my beams wanders a lot, and I cannot use the conventional technique to do the demultiplexing because my beam is keep on wandering. The second issue is obviously the beam distortion because of the various distortion for atmospheric turbulence, or because of the some other issues, and as a result of this, the beam is getting distorted, and once the beam is getting distorted, the negative or conjugate phase mask, if you apply, that technique may lead to a lot of errors. And obviously the other technique is some of the techniques are not scalable, in the sense I cannot apply for all the kinds of beams. As an example, suppose Bessel beams or LG beams or HG beams or different kind of beams. So I cannot scale it out the same technique to all the families of structured light beams. So the answer to this is the AI. And obviously I came to know about this work during the COVID time. And then I founded this beautiful paper, how people have really used it, the AI, for the detection of this OM beam, especially the Zellinger's group, and they did it in 2014. It was the first reported in 2014. So this is to my knowledge, this is the first study based on the AI approach, where they are demultiplexing the structured light using the help of AI. And they have shown that it can be effectively applied, and we can do the OM communication up to 3 kilometers. In the beginning, they have shown in 2014, and then later they have extended to 143 kilometers. In 2016, they have shown. But as I said, and then obviously just to give you our, I can say, new readers, those who are interested in this field, they are very good review article or tutorial written in 2013. Basically, this is the tutorial written in 2013. It gives you a very good, I can say, introduction to how we can able to do the classification of this kind of beam, and obviously how we can use AI for the OM communication. So obviously the technique, whatever they have proposed and further followed by the other followers, the main thing it was, I can say the drawback it was having, since you are capturing the transmitted field and that beam will be very, very big at the receiver end. And then you have to capture whole full mode in order to get the good classification accuracy, and which may not be practically viable for all the time. And obviously the beam distortion is another problem. And obviously these communication is always the line of sight communication because of the laser line of sight communication. In order to overcome these kinds of issue, we came upon something called as speckle based demultiplexing or speckle based recognition of OM. And these are the few works we have published so far, and I will be explaining some of the work from these papers. So what is the key idea? So the key idea is I have some OM beam, and then OM beam is made to pass through the ground glass, which will going to give you the speckle pattern of the corresponding beam. And these speckle pattern, as we know that OM beam, when it's scattered through the ground glass, will have its corresponding speckle pattern, even though visually it looks like a random distribution of the pattern as intensity speckles, but it has an inherent distribution which is carrying the OM information, which our eyes can't see. So then what is the next way? How can I use this speckle pattern to discover what kind of information it carries? Especially here is the charge of the OM beam, which I can use to encode whatever information I need. So then once I have this speckle pattern, which is having the inherent information of the corresponding OM field, and then the advantage of speckle field is that each and every point of the speckle field carrying the information of the OM. So then I don't have to collect all the speckle field. I can collect only a small portion of that speckle field, and this small portion, I will feed it to my convolutional neural network. I will give you a very brief introduction because this audience may not be aware of what is the convolutional neural network. So nowadays, AI is becoming more popular, and as an example, computer vision techniques will heavily rely on this convolutional neural network to classify things or to segment things. So similar kind of neural network, we have used it. First, we will train this neural network by collecting a lot of the spectral images of the corresponding OM mode. Once the network is trained, I can feed any unknown or unseen data to this network, and the network will tell me which OM mode is this. So that is the main key idea, because I was previously working in the speckle field, and I know based on the correlation studies, I can find it out what is the charge of the beam depending on which reference beam I choose. But here it is a reference less. By training the network, I don't need any other references later on. Then I can feed it any unknown, I can say unknown speckle pattern, and then network will tell me which is that corresponding OM mode. So that is the key idea. And how do we realize it? So we realize, as is very simple to realize, we have the Gaussian beam, and then convert it to the LG beam by making use of the phase mask, and then pass through the ground glass. And in order to make it far field, I make use of the lens. I collect the field at the Fourier plane of this lens, and that will going to give me the far field speckle pattern. And this far field speckle pattern, I feed it to the convolutional neural network, and then convolutional neural network will do all the job. Since this audience is not aware of what is a convolutional neural network, I will give you a very brief introduction. It is only one slide, not to divert the talk. So the convolutional neural network works on the principle of the convolution. That's why it is called as convolutional neural network. So as you can see that in the first figure, so whatever my image is this, these images, I will be scanning through some sort of filters. As you can see that, so some of the filters, this is the filters. So these filters are scanning over the image, and depending on the what kind of filter I used, some of the features are extracted. Okay, and once the feature is extracted, it will be high dimensional image because my input field will be very high dimensional. So this convolutional will be slightly lower than the corresponding input image. Once I have the feature extracted, from the feature itself, I will start pulling the important feature out of that feature space by doing something called as max pooling, where I will pick up the maximum among the pixels under consideration. So this is nothing but max pooling, just to perform the downscaling of my data. Because suppose from the input feature space, from the input image, I have the feature space, which is extracted based on the convolutional filter. I scan it. So let's say this is the convolutional image will be like 28 plus 28. And then later on, I will downscale by making use of max pooling feature. So now my image goes down to 14 plus 4. Once I have this 14 plus 14, so I have a various. Hello. Okay, sorry. Shall
Continue,
I
please. This is just noise.
So once I have performed the max pooling, so this kind of operation, the feature extraction and max pooling will have many times depending on which convolutional network you choose. And then in the finally, we'll have a fully connected layer. In this fully connected layer, the final pooling layer, whatever the output I get, I convert into a one particular column. So let's say, for example, this is 14 cross 14. So 14 cross 14 will be converted into 1 cross 14 cross 14. So it will be one dimensional vector. And then this one dimensional vector will be connected to the as many as output as we want. So in our case, suppose if we want 1 to 8 LG modes, then output will be 1 to 8. And this 1 to 8 output will be connected to each and every neuron input, that fully connected neuron. So in that way, the convolutional neural network works. So I keep on feeding the lot of labeled data, just like this. This is the pictorial representation of my convolutional neural network. I can keep on feeding my data, a lot of data to this neural network, and then as I feed it, the filter, the type of filter which is required and the weights which is present over here, it's keep on developing and it will learn to identify which kind of image it is. Or here is basically the classification problem we are doing it. So we are not exactly reconstructing the mode, but we are just telling whether it is a +1 or -1 or +2 or -2, but not reconstructing the +1 or -2 as a field profile. That can be also doable, but now we are not doing. So with this introduction of the convolutional neural, and then just to give you a brief history, that convolutional neural network was basically the structure we will be using is the AlexNet convolutional neural network, and this AlexNet was proposed by Chris Hevsky, and then when I was just googling it preparing for this talk, and I came to know that he's also an Ukrainian guy. So yeah, so coming back to the results, so I have my input field. So input field can be anything, either LG mode, or the superposition of the any LG mode, and these LG modes are passed through the ground glass, and which is nothing but a random phase. And then in the far field, I will get my speckle pattern, and this speckle pattern I feed it to the convolutional neural network. So as I told, I'm using the AlexNet network, and this AlexNet network has, as I said, 5 convolutional layers, which is nothing but the convolutional filter and the max pooling operation. So this will be performed 5 times, and then they will be fully connected layer. And then obviously the classification layer, which how many classes I want to classify. So in this case, I'm doing the LG01 to LG08, only 8 classes. So you can put as many classes as you want. This is just a pictorial representation. Okay, so as I told you, I don't need a full speckle field to classify which mode is this. So once I have the corresponding speckle field of the OM, then we did a little bit of study of the image size versus the classification accuracy. And we can clearly see that when we go down to the, say, let's 128 cross 128 pixels, my original pixel size is nothing but 1024 cross 1024. And then I got an accuracy of, at least these are the simulation results, so almost 100% accuracy. So neural network can easily recognize which speckle pattern is this correspond to which OM mode. And then if I keep on reducing the size of my images, and then when I came down to 128 cross 128, I can still have, I say, about 98% classification accuracy. So it is still doing a better job. And then again, I reduce from 128 to 64 by 64. Then it has drastically reduced to the 90%. So basically, 128 by 128 will do my job. Then in order to quantify how many speckles this 128 cross 128 has it, so we have find the speckle size by doing the correlation study, and we found that in our case, more or less the speckle size comes out to be 10 pixels, and obviously we have 128 cross 128 pixels, so nearly around 10 pixels in each direction. So in that 128 by 128 pixels, you have 100 speckles. So you need minimum amount of speckles to get the pattern out so that it can easily recognize which OM mode is this. So if I put a ratio of speckle size versus the full image size along the horizontal or vertical, it comes out to be around the 1/10 ratio. So that will do a good job for the classification. So these are the results we have performed. So at least for the simulation results, we got almost 100% accuracy. But in the experimental result, these are nothing but we have achieved the different phase mask based on the ground glasses. These are the different grids of the ground glasses. We have used 3, 120, 600, and 1500. And then obviously, in the beginning, we have trained independently. And then later, we have combined the whole data. And if we combine the whole data, network learns much better as compared to we will do it individually. And in order to test the robustness, suppose if we train the network on, say, ground glass 120, these are only the experimental accuracies, because just to test what is the generality on the experimental data. So if we have a data based on the ground glass 128 grid, and then I trained it, and then I test it on the ground glass data, which is I get it from the grid 600. My accuracy is very poor, because obviously this speckle field generated because of the 120 will have a different speckle sizes and different features, which is network is learning only these features, not the features because of the G66 ground glass grid 600. But if I incorporate the number of ground glasses, then I can see the accuracy has went up. And if you see in this case, it has went to 92%. So I'm just feeding my data generated because of the ground glass 120 and 1500, and I'm testing on the data which is generated because of the ground glass 600. So as you can see, it has reached to the 62 because I have a maximum variation in the data, because G22 will going to produce the maximum speckle size, and then G150, 1500 will going to produce smaller speckle sizes of OM modes. So therefore, I have a maximum variation in the data. So maximum variation, you give it to the data, then better the network learns and it can do the classification much better. So even though I'm feeding the data with the unseen, with maximum variation will going to give you the maximum accuracy. And then in further, we have also did a simulation study on the atmospheric turbulence data. We have simulated the atmospheric turbulence, and then we have again, so whatever the beams we got out of the atmospheric turbulence, we we can directly do the image classification on this data itself. But as I said, because of the distortion, network may not learn all the time. It can be made to improve based on the different AI techniques. There's something called as reconstruction technique, but we will not focus on that. So now if this distorted images, if I again feed it to a random ground glass, so now it will be going to produce the speckle pattern. And this speckle pattern, as I told, these are basically nothing but the network will going to capture the features of corresponding to the corresponding OM mode, and they will learn based on the feature, not on the noises which the OM mode has. And we have achieved, at least for the simulation data, we have achieved, this is for the individual modes, we have achieved an accuracy of greater than 98%. And for the superposition mode, we have achieved accuracy of 94%. But now coming to the intensity degenerate modes. Obviously, the modes with plus and minus 1 have a I can say they are the intensity degenerate modes, plus and minus L. And even these far-field speckle pattern also have a very, I can say, closed distribution, which neural network may not able to sense it to classify it. When we did this study, we were just using the inbuilt Fourier transform command to get the far-field pattern. And that inbuilt command does not capture the real, I can say, manifestation of the corresponding charges. So our network fails to organize, fails to recognize the plus and minus charges. So as you can see, the maximum, I can say, disclassification happens between the plus and minus only, but it can able to classify very well the other charges. Similarly, the superposition of intensity degenerate mode, same problem. And then even the perfect vertices, also the same problem. So how to solve this kind of intensity degenerate modes or classify the intensity degenerate mode using our method? So as the answer comes to, it's already there in the literature, is nothing but the astigmatic transform. And in the literature for the mode, if you do the astigmatic transform, and that can be by performing the astigmatic transformation, I can easily recognize what kind of OM mode is this. The same thing we did it for the speckle pattern. So instead of performing the 2D Fourier transform, which we did it in the last time when we did it for the Fourier transform, when we get the far field by making use of the Fourier transform, we perform the 2D Fourier transform. But here, since we want to introduce astigmatic transformation, so instead of performing the 2D Fourier transform, I will be performing the 1D Fourier transform, which will be analogous to the cylindrical lens case. So this is my intensity degenerate modes. And then obviously, if you see the 2D Fourier transform, they look visually very similar. Even the CNN, which we have it also is not able to classify which mode is this. But when we do this kind of transformation, which is one-dimensional Fourier transform, which I can easily realize experimentally by using a cylindrical lens. So my speckle pattern will able to classify, or the network will easily sense depending on the astigmatic transform speckle pattern, which kind of mode is this. So by introducing the astigmatic transform, I can easily able to classify the intensity degenerate mode as well. And in order to test the robustness against the noises, so one of the case which I have already demonstrated is nothing but the atmospheric turbulence noise. The other noise which we have simulated is nothing but the Gaussian white noise, which I can easily do it. So on the mode, I have intentionally introduced the Gaussian white noise for starting from 10 dB to minus 10 dB. This is the minus 10 dB. If you can see that this mode looks very distorted. And then obviously I can do the astigmatic transformation, either the symmetric as well as the non-symmetric. And depending on the what kind of astigmatic transformation I perform, I'll get a corresponding speckle pattern. And this speckle pattern I will be using for the classification. I will feed it to the convolutional neural network, and that will do a very good job. So just to give you the simulation results of this study based on the Gaussian white noise, starting from 10 dB to minus 10 dB, and you can see this LG mode, it gives very good. If I perform the 1D Fourier transform, which is based on the astigmatic transformation, it, at least the simulation result, it shows a very good classification accuracies. And 2D transformation, which is nothing but 2D Fourier transform, it fails to recognize this. These are the nothing but for LG mode, and similarly for this is superposition mode, and this is nothing but the perfect optical vortices. And even in the case of perfect optical vortices, it has performed a very good job. And along with the noises, you can see the 10 dB noises is going to 98, and then at least the minus 10 dB, it is going greater than 64%. This is simulation result. Obviously, we have to perform the experiment, but at least more than that, it gives you a very good, I can say, idea that these techniques also preferably can apply to this kind of very high noise system as well. And then we have later on, we have implemented this kind of study to perform the OM shift key. So in this OM shift key, we have encoded a 4-bit grayscale image into the corresponding OM degenerate modes. We have chosen from LG0 -8 to +8. So we have total 15 modes, excluding the 0, LG00, which is nothing but the Gaussian. So we have a 4-bit correspond to 2 raised to 4, which is 16 level. So this 16 gray level, I will be encoding in LG0 -8 to LG0 +8. And these are intensity degenerate mode, as I told you. And these degenerate modes I will be forming with the help of Fock hologram. And once this OM mode is generated, then I will introduce the Gaussian white noise to introduce the noisy channel. And then once I have the corresponding distorted mode, and here the level which I kept is nothing but -10 dB of noise we have introduced. And this 10 dB noisy Legare Gaussian modes are then passed through a random phase creep and then introduced by a astigmatic transform, which is nothing but analogous to a cylindrical lens in experiment, or we have performed the 1D Fourier transform. And this speckle pattern, whatever we got it, we fed it to our convolutional neural network. We first trained it with a lot of data, and then later on, once the network is trained, then we can do the OM shifting. So whatever the pattern we get it, the network will tell which kind of OM mode is this, and then we do the back mapping from OM mode to the grayscale, and then we reconstruct the image pixel by pixel. In this way, we have implemented the OM shift key. As you can see that this is simulation result, but later on I will going to present the experimental result as well. But in the simulation result, it has exactly replicated my input mode and the receive mode. And now based on the intuition, we got it that I don't need a full speckle pattern. A small portion of the speckle pattern will do the job. Based on that ideas, we have tried to implement something called as non-line of sight optical communication, which is not at all possible for the optical communication, because wherever the laser is present, there is the communication happens. So generally the laser communication is nothing but the line of sight communication. But based on the principle of the speckle propagation, as we can see that when the laser falls on the ground glass, it will produce the speckle patterns, and this speckle pattern will be forming a cone, and it is propagating by making a cone angle. And then range of the cone angle depend on the how much is the scattering efficiency of this ground glass, and what is the grid, ground glass grid, or nothing but your what is the minimum phase gradient these ground glass has. Depending on that, the cone angle will be decided. So in our case, the cone angle is reaching about to be 30 degree, 15 degree on both sides. So total cone angle will be nothing but your 30 degree. So we have captured the speckle pattern at 3 different channels. So one will be the on-axis channel, which is we call it C2, and the second and first and third channel will be at an degree of 15 degree with respect to my on-axis on-axis beam on axis. And I captured my speckle pattern at this angle. So along this whole, I can say, region, I can do the non-line of sight communication wherever I'm able to capture my speckle pattern. As I said, I don't need all the speckle, sufficient speckle will do the job. So therefore, the range of the non-line of sight increases depending on the wherever the speckles are present. And so here we have demonstrated 1 to 3 channel. So we have first we have implemented using the Hermite Gauss beam, and later we also did it with the LG beam also. So in this case, we have taken Graham-Bell's images, 3-bit scale Graham-Bell's images. So it has 2⁻³, nothing but 8 gray levels. So you can see this white to black. These are the 8 gray levels, and these 8 gray levels we are encoding in different HG modes. And these HG modes we are generated using the SLM, and then we are getting the speckle pattern after getting the scattered from the ground glass. And at the 3 different channels, I will able to collect the speckle patterns, and then I train the network, my convolutional network, and then once network is trained, and then I can send these images, and then depending on the whatever speckle pattern I'm getting it, I can simultaneously reconstruct these 3 images at these 3 different channels, C1, C2, C3. As you can see that classification accuracy is maximum along the on-axis channel, which is nothing but the 96%. And off-axis channel C1 and C2, C1 and C3 has a lower accuracy. And this is basically because of at the off-axis angle, your intensity goes down. So your signal to noise ratio is degrading, as a result of which your the classification accuracy goes down, but still it is quite good enough. And here we are doing the free space propagation. And so here we are just collecting the speckle directly coming out from the ground glass. I can improve this accuracy based on the, okay, so before that, so the question comes is, if I take a line profile along the speckle in any particular direction, either this direction or this direction, I can see a symmetric isotropic distribution of my speckle pattern. So if I take a line profile across any randomly chooses orientation, this, I can see my speckle pattern looks like this, which is almost visually looking the same. Since it is isotropic in all possible direction, so can I use only the line profile instead of a 2D image to do the classification? Answer to that is yes. So we perform that kind of analysis. So we have taken a speckle pattern, and then instead of taking the full speckle pattern, so in this case, my speckle pattern will have a size of 1920 cross 1200. So it is like almost like 2.3 million pixels. So it is a huge data. But instead of taking so many pixels information, if I just take a line profile across randomly selected orientation, then this 2.3 million pixels, instead of taking 2.3 million pixels, I will consider only 1 cross 192, 1920, which is nothing but only, I can say, 1 by thousands of my original data. And these data, I will feed it to my convolutional neural network. But in this case, the convolutional neural network is not 2-dimensional, it is 1-dimensional. And just to add up that, before feeding the data to the convolutional neural network, I extracted some feature. So I just give little help to the convolutional neural network by doing some pre-processing in the data itself. That I can do it, or I can build a deeper, because in the beginning, now we are able to do it a deeper 1D CNN. Previously, we were using only one convolutional layer in my convolutional neural network. So my network is not deeper enough to learn the feature. So in order to make the network learn, we are giving the feature itself by using some feature extraction technique. There are a lot of feature extraction techniques are available. So one of the technique is nothing but the wavelet scattering. Just to tell you, wavelet scattering is similar to kind of a Fourier transform, where instead of using sines and cosine, we use the wavelets. So there are a lot of wavelets exist. So we will be using here, we have used the Debussy's wavelet to do the corresponding transform, wavelet transform. And then the extracted feature is fed to the 1D convolutional neural network. And this 1D convolutional network quickly learns, and then it is able to classify the whichever mode is this, either it can be HG as well as HG, based on just the 1D speckle profile. Okay, and then these are the corresponding results. We have it. These are the 2D based on the full image. So you have across the I can say on-axis channel, we achieve an accuracy of 96 and off-axis 92 and 93. But with 1D, only 1D information, I got the classification accuracy along the on-axis channel 72. It has dropped a little bit. And then later on, we'll see how to improvise. And then off-axis channel we got it 69 and 49. These are all the experimental data. These are based on the HG mode, and these are based on the LG mode. So these are the intensity. So in this case, we have considered only the plus LG modes from LG01 to LG08. So in this case also, we got a similar accuracy what we got it for the case of the LG modes. But for the case of intensity degenerate mode, this 1D line profile doesn't work. 2D, obviously it works, but 1G, it doesn't work. This is experimental data. As you can see, 2D, we have introduced the astigmatic transformation. Since experimental data, we will have some kind of inherent astigmatism. So network learns based on that inherent astigmatism, and it is able to classify it well. But for the simulation data, it is not able to classify. So now coming back to the how to improvise this one-dimensional classification accuracy based on the 1D speckle data. As you can see, the classification accuracy is very, very low. The reasons is because we will be using a free space propagation, and with free space propagation, obviously the speckle will be dying off. You're losing the lot of data, and then your signal versus the noise ratio is also coming down. So as a result of which, if you are going from 2D data to 1D data, obviously you are losing a lot of information. So in order to overcome that, we have used a lens to collect the speckle coming out from this ground glass, and then in the Fourier flow, in the Fourier transform plane, we collect the speckle. Now we were able to get, by performing this kind of operation, and then obviously since we are using the lens, so generally it will work for the only on-axis condition. So previously when we were doing the on-axis case, we have achieved using the 1D speckle information, we have achieved the maximum accuracy of 72. But by making use of the lens, so that the collection efficiency of the speckle has increased, and as a result, we have achieved accuracy up till the 89%. And again, we performed the OM shift key, and we were able to just reconstruct back our images just based on the 1D speckle profile. So in order to conclude the talk, so as we can see that obviously I don't have to explain why this OM will going to give you a high spectral efficiency, because obviously it is infinite. OM has an infinite dimensional space, so therefore I can have the higher dimension. The spectral efficiency will be as high as possible depending on the high dimensional space I used it. And as I told you, it is alignment free, because my speckle pattern, I don't need to align it to produce the speckle pattern. It can be easily produced even if you tilt the ground glass. In that scenarios also, it will do the classification, but you have to introduce all those kinds of manifestation in your trained data itself by collecting the data with all this kind of distortion. Then only the speckle, the convolutional neural network learns, and it will give you a better classification accuracy. More the variation, better would be the classification accuracy. And it is only the intensity based. I don't need any kind of reference. And it's a single shot. After once the network is trained, just by intensity based single shot, it will do the classification. No need to capture the whole mode. And I can even perform based on the 1D line profile of my speckle pattern. So my amount of data requirement has reduced one by 1,000 in our case. And obviously, once your data is reduced, I can perform this kind of thing in my laptop as well. We did it. I don't need a GPU-based computer to train my neural net. So obviously, with this, I'll just thank the funding first. So I need to acknowledge the SERB and then the Professor Nirmal K. Vishwanathan for allowing us to use his lab facility, as well as the Professor R.P. Singh, because we don't have a lab facility here. We are building our lab. And then as of now, we are relying on them. So we are really helpful to them to allow us to use their lab facility for the experimental data. And then with this, I'll thank you. And these are my students. And the work which I presented is mainly started with this MSc student. He's a very brilliant MSc student. His name is Venugopal. And currently he is doing PhD at Southampton with Professor Nikolai Zaludev's groups. And then his work is followed by my PhD student, Mr. Purnesh. The null nanofert work is done by him. And this is Chainika, another PhD student. She is currently pursuing in that direction. And these are the MSc student. They also did some work on the astigmatic transform, and they have a presentation in the JSAP, which is nothing but a conference which is coming day after tomorrow in Japan. They are presenting online. And she's Trishita, MSc student. She also did some structured light based demultiplexing based on the LG mode. In that case, she's using the demultiplexing technique. Here we have shown only the OM shift key, which I needed like lot of modes depending on the bit size of my image. If I have a bit size n, so I need a 2⁻n mode, but that I can drastically reduce by changing the demultiplexing technique. So with this, I'll say thank you. Hello?
Okay, questions, please. Comments? I have a question. Your operations, when you need for some time, what is the duration of your operation? The last operation when you do the convolution in the neural system.
Yeah, convolution. So as I said, because the network will be trained based on the convolutional operation, and these operations are very, very fast. So in the beginning, I need to train with lot of data, and then depending on the data, these convolutional filters will be generated. And when I train it, obviously it will take a lot of time to train it depending on the how much data I have it. But once the network is trained for doing the demultiplexing, suppose let's say one image of some OM mode comes, and this OM mode can do a very fast demultiplexing depending on what is the complexity of my neural network. As I said, if it is two-dimensional neural network with, let's say, 5 convolutional pooling, then it takes like millisecond or so. But when it comes down to one-dimensional case, the classification will be done in a, I can say, in a microsecond range. I can do it.
Thank you. More questions? Thank you again for your nice report. And now the next report by Desyatnikov from Kazakhstan, Vortex rings, reconnection in Gaussian laser beams. Please.
Hello, everyone. Let me share the screen. Hope you can hear me.
Yes.
All right. Can you see my screen and all working fine?
All is okay.
Okay, thank you very much. I'll just use the laser pointer. This talk is with our graduate student Jamila Kulchukova, who is also in the audience, and we are from Nazarbayev University in Astana, Kazakhstan. And today I will be talking about optical vortex rings. And of course, in a talk like that, I will mention the knotted rings and vortex knot. But my motivation would be based on a picture from Born and Wolf, which I'm sure that everyone saw it before. And however, the system that I will describe is embarrassingly simple. I'll be just talking about the destructive interference between a plane wave and different Gaussian paraxial beams. My only excuse is that, well, to me, there is some unexpected complexity, so I hope that this talk will not be as trivial as it sounds. The first part was published actually last week when we talk about the radially symmetric beams like Gaussian and vortex beams. And the last part, Jamila is working hard on that, finalizing the draft, and it's with elliptic and astigmatic beams, and I will talk about our motivation, why are we interested. So let me start with Born and Wolf. I saw this picture in the book, and it appears from first to the last editions for 40 years. And in the first edition in 59, it was very fresh from the print in 1956. Of course, the picture was very important in a sense that it shows the complexity of the non-paraxial strongly focused, the structure of the strongly focused light near the focus, but also it is diffraction on a circular aperture, and the link is direct to airy rings. And this phase anomalies at the rings, at the dark airy rings, were recognized and connected with the GOI phase anomaly. So I think it's kind of a very important paper in the sense that it links to fundamental phenomena discovered 100 years before the paper or so, but also discusses a very important focal parameters that are important for resolution and applications. Right, so we're talking about dark rings, and it didn't take long, 10 years, to recognize that those rings are actually vortex rings. And in the paper by Voycehovich and Wolf, they call it an optical vortex. I must say that, you know, these important pictures in the 50s and 60s, I can hardly imagine today that, I mean, I've done it myself by hand in the 90s when I didn't have good computers, but I will definitely bring it to the attention of our students that at that time, every paper like that ends with the special thanks to professional people who actually did the figures, right? So you calculate the tables and you do the figure at the end. Quite interesting. Right, 1967, it took another 30 years till the singular optic developed that the importance of the phase singularities were recognized. And I quote here the paper of Professor Berry, studying how these vortex rings reconnect when we go from non-paraxial to closer to the paraxial regime. Because we know that paraxial Gaussian beams, they are dislocation free. That's what I want to emphasize. In non-paraxial systems, these dislocations, the vortex rings in particular, the airy rings, are given for free. They're kind of present there. And I quote again Professor Berry saying that the interference, for any dislocation like that, we need destructive interference. And here's the interferences between the complex ray and marginally evanescent waves. So that is the origin of the dislocations in non-paraxial fields. Okay, right. When we talk about yes, and so singular optics, of course, very quickly the vortex not followed, and again, originally Berry and Dennis introduced it in a non-paraxial system. Very important step to distinguish the two systems, paraxial and non-paraxial, was to prove the little theorem, but kind of important, that the Helmholtz equation supports higher order vortex rings. The Schrödinger equation does not, right? And so you would immediately say that higher order dislocations are not stable in the Schrödinger equation. That did not prevent constructing vortex knots, as we all know, and the theoretical and experimental development followed very quickly. And I hope I will not say anything, or Mark will correct me if I say that the key to construct vortex ring and then knotted vortex rings was very elaborate superposition of paraxial Laguerre-Gauss, for example, beams, right? So it's a multiple beam interference, but in every paper that Mark and Miles wrote, it's algebraic topology embedded in the laser beam using spatial light modulator. It works, and of course it's proven it works. It's just that in non-paraxial system it's given naturally for free. Here we have to make a special effort. So that's what I'm wondering, if paraxial system could offer some natural, some generic vortex ring. One way is to use a multiple wave interference, and Mark yesterday talked about isotropic random waves as a superposition of multiple waves, and there were studies of in paraxial regime as well, when the multiple wave interference, of course. But here the complexity kind of expected, because you make it complex from the beginning, right? It's a random superposition of many waves. Can we do better? Can we do simpler? That's one of my motivations. Another comes from our studies in nonlinear singular optics, studies of spatial solitons. In particular, a few years back, we discovered theoretically, numerically, that a very well-studied phenomenon of self-focusing, it's actually accompanied by a vortex ring, right? And the reason for that is that the nonlinear phase, when it accumulates during the propagation, there is a phase difference accumulating between the soliton, the laser beam maximum intensity, and the low intensity tail. So it happens spontaneously, generically. It's given for free like that, okay? And also it can lead also to spontaneous knotting of these rings. Later on, we've done some more simulation in so-called non-local, non-linear medium with the group of Alexander Yakimenko from Taras Shevchenko National University in Kyiv. And the mechanism is very robust, but we also discovered some rings that keep bothering me because we didn't have a good explanation for them. And I thought that if I lack the understanding of what's happening even in linear cases, this Gaussian beam. So this is another part of my motivation. I want to understand what happens in linear case and then apply it to non-linear case. And you would think that, or I thought that, for many years of singular optics, somebody's done it, but I couldn't find it. And so that was the motivation of why study the superposition. Yeah, just to finish, yesterday, Kostya Blioch was talking about his collaboration with the group of Milchberg in US, and but I just wanted to say that the first experiment on spatiotemporal optical vortices they did was actually nonlinear propagation, and so this mechanism which I just described of spontaneous generation of a vortex ring was actually present there, and that's their first spatiotemporal vortex rings generated because of nonlinear interaction. my understanding is that later on they just started to build deliberately the setup to generate those special temporal vortex rings, forgetting about the nonlinear, air ionization, but very strong focus pulses and so on, which initially led to. So robust mechanism, they appear spontaneously. And in that sense, they are generic the same way as in non-paraxial fields. In non-paraxial fields, as I said, the interferences between, again, quoting Professor Berry, between a complex array and a marginary evanescent waves. In a linear system, I talked about optical solitons. However, the same mechanism applies to superfluids, such as Bose-Einstein condensate in the nonlinear regime. And also, if you remember smoke rings or vortices in viscous fluids, it's also hydrodynamics is highly nonlinear system, right? So kind of expected. In paraxial fields, we do have speckle fields with a very complex topology, and we do have a route to generate deliberately vortex rings and vortex knots. But there is this obvious difference, and I wanted what paraxial fields can offer. Is there something that we miss? So here's our system. I'll take paraxial wave equation and this index 4 before I might be unusual, and that's because if you do that in this representation, the solution is extremely simple. If you need to work with field, not intensity, that's the simplest expression I got. That is why we use 4. What do I want to do? I want to do a superposition of this slowly varying envelope E in the around the italic E electric field. You can see I have a propagation factor K, the wave number, and I superimpose it with a plane wave which has a real amplitude P and arbitrary beta phase. But also I'll mention the counter-propagating case, because you see the idea was that okay, I need to generate the phase difference, and if for example the phase which is available in Gaussian beams, which is dynamic phase and geometric Bowie phase, will not be sufficient to generate singularities. Maybe the strong phase difference generated in counter-propagating beams will work. So I will mention that, but I will not focus on that. Right. So the task, as we said, it is just find field zeros, and that's the equation to solve. And here is phi is this relative phase. Pi is there, so when the phi is 0, it means that the two waves are out of phase. Okay. Right, this is the system. There are different ways to solve. For example, the nodal lines are crossing of the real particles here and imaginary particles as surfaces. But here we choose to do amplitude and phase separately. That's the system of equation. And we will normalize the maximum of our Gaussian beam to 1 so that P is a relative amplitude and we have relative phase, 2 key parameters, right? The Gaussian doesn't have any parameters left because we all scaled away the transfer scale, everything. Right. So if you look at the focal plane and we say, okay, well, Gaussian beam interference with the plane wave, what could be simpler? We have a dark ring, and yes, it's a vortex ring. And when the amplitude of the plane wave goes to 0, this dark ring just goes to infinity. Very kind of intuitive and expected. However, what happens in the bulk? That's a little bit more complicated, right? So in the bulk, the phase, and here's the dynamic phase, and here's the Bowie phase, play a role, and of course, they will influence where do we have destructive interference, right? So this is the system of equation. The first of it just give us the kind of iso intensity contour levels for Gaussian beam. Very well known. If the amplitude is greater than 1, there are no zeros, but then we decrease it P below 0, and we have those surfaces. I will call them spheroids, just because there is like deformed sphere, and it's different from toroids in the next section when I talk about vortex beams. Right. So when we decrease P below some value, we have the shape changes with 2 maximum. And the important for the following, so this is, I mean, another thing which is fun here is that, of course, everything is so simple that a lot of analytical results can be obtained. Right, the dashed line is what people call beam caustic, which is the beam width. And the crossing of this dashed line with the ISO intensity contours will be also important. So that is one example of what we have. The gray surface is the caustic. The bluish surface is this spheroid at which dislocation leave. And for some particular phase difference different from 0, we have the vortex ring shifted from focal plane. Kind of expected. Nothing super dramatic. I will run the simulation just for you to show how it appears. So we fix P and we just scan relative phase. Okay, that actually brings me back to the talk by Professor Brasselet yesterday, because the relative phase here can be organized to run in real time. Just if you introduce a small frequency difference between the two beams, right? So if we introduce the frequency difference of 1 kilohertz, the speed of this vortex motion would be around 1,000 diffraction lengths per second. So if anyone needs a fast-moving vortex, optical vortex rings, that's the probably simplest way to do it. Okay, decreasing a little bit the plane wave amplitude when the shape develops, and you can see how this spheroid crosses now the hyperboloid, the caustic. That plays an important role here. Let's run the phase. The rings just bifurcates from the optical axis. That's one thing happening. But another thing happening is the pairwise bifurcation of 2 rings with opposite circulation. And then symmetrically it goes and annihilates like that. Okay? Just I will run it again just to notice where it happens that the pairwise nucleation of 2 rings happens exactly where the hyperboloid crosses the spheroid. And I don't have a good explanation why it happens exactly there. Okay, what happens? The vortex ring, which appears kind of outside of, so with the radius greater than the hyperboloid, the caustic, has opposite circulation. The energy flow shows it here, but we can also calculate it explicitly, and that's how the vorticity changes the direction. You can see in these pictures I plotted the current for the total field, but this is called the co-propagating beam. So the factor of Kz is taken out, and the flow is kind of backwards. And the reason for that is that close to the axis, of course, we know that the Bowie phase dominates and it's negative. Not only it's negative contribution, it has negative gradient. And as a result, this part of the flow is backwards. The total flow, of course, is forwards when we add Kz. Important to realize is that when we add Kz, the location and handedness of vortices do not change. So removing Kz from this picture doesn't change the topology of the thing. Although the current looks really distorted and those vortices are really distorted. Anyways, moving forward, decreasing P further. I mean, from the simple picture that I showed at the focal plane or intuition, you would expect probably that, you know, taking a small p as a small perturbation, everything what happens should move and disappear at infinity. Kind of does, because if you see those black dots and white circles are vortex rings, and if you want to find a vortex ring within the relatively high, close to the peak intensity of the beam, you can. It's just you have to go further from the focal plane. If you want to find them close to the focal plane, you have to go to the dark, but not really far. like two waste parameters, and that's where they concentrated here for the small p. So this picture that all the perturbation, when perturbation vanishes, you know, all these rings should go and disappear at infinity is kind of true, but it's not as simple as it looks like. That is the key figure now I present to you. It's a phase diagram in the sense that there are two key parameters: relative phase, relative amplitude. But it also separates this region parameter domains with different number of the rings. So the numbers inside the domain are number of the rings that we have in Gaussian beam. So the first one, this mechanism that the ring will just bifurcate on the optical axis, is this dashed line, right? And it happens, so in parameter domain, when we cross this line, the number of rings changes by 1. And those are bifurcating or annihilating on the optical axis. It happens at this extreme points on this spheroid. The second black line, the solid line, corresponds to this pairwise bifurcation of vortex ring pairs, and crossing this line in the parameter domain changes the number of rings by 2. Now, of course, the first mechanism is robust. The second one is non-generic, because you can imagine that any deformation would destroy it, and that would be our motivation for the following parts that we have. Well, one more notice here is that everything is linear in 1/p. And so when we estimate the number of the rings, the trend line is also 1/p. You can see that no matter where we are, each topological event happens exactly once when we scan the relative phase, right? So we have one bifurcation on axis, one annihilation on axis, pairwise bifurcation, pairwise. So that is the story about the vortex rings on circular symmetric Gaussian beams. Let me move forward to the vortex Gaussian beams. And I do not take any radial modes here. And also I normalize the vortex envelope to 1 just to have it consistent with previous. Right. So when we solve the first equation, the amplitude equation, it's clear that there are two roots, and we can distinguish the two surfaces where the dislocation can appear. The second equation for the phase would define those, but they only can appear on these black lines here, black lines, which I will call spheroid. Oh, sorry, toroids. So these three different toroids for charge 1 and charge 3. Without any limitation, I will use the positive, non-negative charge L, right? Okay, so we have two roots, rho 1, the inner surface, and rho 2 is outer surface of the toroid, and they join at this dashed line, which are hyperboloids corresponding to the maxima of the vortex ring envelope. It scales as square root of L. However, when we normalize it's interesting that the extent where they go does not depend on L. And it's exactly the same how far those surfaces go. It's exactly the same as with the Gaussian spheroids and Gaussian. So that's probably the only common thing between the two types of beams. Right. That is how a vortex ring look like when we interfere a single charge vortex beam with a plane wave. The amplitude of plane wave is relatively large, p equals 0.6. The ring, I put it on this toroid and cut toroid to help the eye. And also I color two parts of the rings, yellow and green. They belong to different surfaces of the toroid, outer surface, inner surface. It just helps the eye. What happens with the angle when we solve the location of the vortex line? The equation is here, and you can see that in general, this rho S index distinguishes this inner and outer surfaces of green and yellow part of the same vortex ring. And in general, they should be different here. P is large, and the ring is just gently twisted, and it twisted counterclockwise. Positive charge counterclockwise seem to be consistent. Right, that's what happens with the charge 3. Of course, we expect that the higher order dislocation splits into 3 vortices, but actually those are 3 vortex rings. And now the color just distinguishes the different rings just to help that. This little movie is obtained by scanning the relative phase. You can see here in the expression that the relative phase just plays a role, trivial role of the. But again, if we change it in real time, we could make it very fast vortex ring propeller beam or something like that, right? Okay. What happens if we further decrease plane wave? And the plane wave would decrease and vanish at some point. We would expect that we would restore the original vortex beam. And indeed, the green line comes closer to the axis. You know, and for a few diffraction lengths here, it's just on axis. And it's still twisted counterclockwise in the positive direction. But look at the yellow part of the ring. Now it is twisted clockwise into the negative. And the explanation is this. The closer to the axis, the diffraction phase, the dynamic phase, can be neglected. And so on the inner surface rho 1, which comes closer to the axis, we can neglect with respect to the Gaussian phase. And Gaussian phase gives positive contribution. What I'm saying? Yes. Positive contribution to phi, which is counterclockwise direction. So the green line turns counterclockwise. The yellow line is on rho 2 part of the toroid, which is large, and the dynamic phase gives negative contribution, which is clockwise. And so the ring is kind of twisted in different direction, and we can see the interplay between the dynamic and geometric phases. That is the picture for charge 3, which you already saw in the opening slide. And of course, to be honest, that's not what I expect. I did not expect this complexity, and asymptotically, everything moves to infinity, but asymptotically, the twist angle of the outer part of the beam of the vortex rings also diverges. I mean, it goes, of course, it goes on a larger and larger scale. Here on the bottom, the scale is from -10 to 10 diffraction lengths, but still the angle is quite large. Right. So another little movie to show you how I am actually running out of time. Am I? Hello? Hello?
You should probably wrap up in a couple of minutes.
Right, and I missed the whole part of. Okay, thank you. I missed the whole part of. So I'll jump. Right. So this is how the vortex ring in a single charge vortex beam grows, and as soon as p the angle of rotation diverges. Right, guys. This is the quick jump through counter-propagating beams. I didn't expect to spend so much time. Sorry. But I will just run quickly through some conclusions that we have on elliptic beams, and we distinguish purely elliptic profile, astigmatic beam we use to play with the Gaussian phase in X and Y direction. And those beams, they give us, this is fresh results, not published yet, and Jamila is working hard on them. And those things give us the vortex reconnections, the new phenomena which we did not observe in the radially symmetric beams, the vortex ring reconnection. For example, here, this is an example when a pair of vortex rings transforms and reconnects into another pair. Here is the movie how it happens in elliptic beams. So 2 and 2. Here's another example, the same, but following different trajectory in the parameter space. Parameter space, as you can see, as we break the symmetries, we obtain new and new complex features. And those lines which were clearly, separating the burst or reconnection of vortex rings, they change their meaning. And we have few peculiar cases where the reconnections happen on different scales. So here is across the whole beam, and this is reconnection 3 rings to 1. This one is also 3 to 1. I've just shown slowly the same picture that you saw. Okay, let me jump through a little bit to simpler cases. That is the astigmatic and elliptic beam when we play with both parameters, astigmatism and ellipticity. And here is a bit more complex reconnections, 4 to 2. That's how it happens when we scan the parameter domain. 3, 5, 3, and the same lines which used to play a role when they change in the number of vortex rings. Now they play a role without changing them. All right, I have to wrap up, and I think the takeaway message is that very simple system, and it's simple analytically, but also I hope that will be accessible in experiment. However, it gives kind of unexpected complexity. There is we can visualize the interplay between dynamic and geometric phases. And also what we are busy with is trying to understand how the breaking of the symmetry gives us the new topology in vortex rings and reconnections. Thank you very much. I'm sorry I'm over time a little bit.
Thank you very much for the nice report. Questions, please. I have a question. If we have the vortex ring which is positioned perpendicularly to the optical axis, can we say about the back direction of wave propagations due to the specific energy currents around the vortex?
You can distinguish the vorticity. I'll just go back to just find this picture. Where was it? I had the picture is the current. Here it is. I'm not sure if I answer by saying that, look, we can distinguish the vorticities of two. I mean, you can use the right-hand rule or something that when you choose direction along the ring, how the phase goes, and then you distinguish the two vorticities. And then they of course define the current. Did I answer, Professor Mokhun?
I see. Thank you. This is a complex question and a hard question. Thank you. More questions? Thank you again for the nice.
Thank you very much.
Talking, and now we continue the report of the Professor Vasnetsov from the place where he stopped.
Okay, do you hear me?
We are listening you, but
okay, I do share screen, and probably you see the picture.
You have only a few minutes.
Okay, so in a very brief manner, I will speak that we modified our experimental setup to observe the scattering along the angle about 35 degrees. And we changed the temperature, so it's the change in the spectrum. And what we got the very, very pronounced difference. So at room temperature, we have the speckle pattern, but it was smooth at this 45 degrees. And in a quantitative manner, we can measure the visibility, which is always unity for the speckle field because the minimum value is 0. So at room temperature, we have about 92%, and at this three chromatic illumination at the angle of 35 degrees, we still have some modulation, some speckle modulation, but we removed zeros, we removed vortices. So we got a victory over vortices and killed them. You can ask me where they exist now. I can explain if you ask me. Well, and some conclusions. So the result is a little bit paradoxical because what we did, we influence on the temporal coherence, but received a special overlapping of this speckle patterns and the smoothing of it. It could be used in laser microscopy or laser tomography. The second question, how to remove the speck pattern in the direction of the beam. And what we will have instead, if you use instead of the thin diffuser like ground plate, a long wave diffuser like atmospheric turbulence. So we are going to check this issue, and I believe on the next conference I will report on the topic. Thank you.
Okay, questions, please.
Hello, I have, if it possible, one question, please. I repeated in the chat, but I want to ask a more specific question about the length of the coherence of the laser that you used in your experiment. And other one question, what is the fundamental difference between speckle pattern observed in low coherence optical fields and the fully coherent fields? And
well, so the picture is here. Was very surprised. We measured the coherence length for this single mode operation. So we measure that it generates at the single mode because the cavity is very small. And we just got fringes with a difference, with optical path difference about 5 meters. So it could be longer than 5 meters. Then for this 2 lines operation, we also got the fringes at about the same. So actually, we did not measure the coherence length because it's very high.
thank you so much. Thank you.
Okay, Steen, your question.
Yes, thank you, and thank you, Professor Vasnetsov, for a very good presentation. I just had a small argument that you have a kind for a certain angle with respect to your surface. You have a repetition of your speckle pattern, and that has, for our use, been used for optical wave meter, and I'll be happy to send you some papers on it because it's very interesting what you're doing. Thank you, Professor Vasnetsov.
Thank you.
Okay, thank you very much. Maybe we will close our section because we must go to the lunch. This is a very important
Yes,
event.
thank you very much, everybody. Now we had a break. We have a lunch until 2 p.m. At 2 p.m. we'll start the second session. The co-chairs of the session, Professor Hansen and Professor Dieterland, And the first speech will be presented by Dr. Neglic at 2 p.m. Please use the other link for other second session. Thank you.